Ladies and gentlemen, welcome to this dedicated session on transport applications and refueling infrastructure. You will have the pleasure to hear about results coming out of 7 projects, most of them supported by the FCH. We'll be talking about cars, buses, and hydrogen trucks in that order. And I would like to give the floor to Lisa Roux from Element Energy, who is the coordinator of project H2ME, H2ME2, and Zephyr. She will introduce to you an overview about this project, and then it will be followed by a presentation about the data collected from this project made by Mr. Victor Lerona from Cenex. Lisa, the floor is yours. Thank you.
Good morning, everyone, and thank you, Lionel, for this introduction. I hope you can see the slides on screen. Let me know if that's not the case. I think I cannot see them myself. But if we could move on to the first slides, what we wanted to give you is an overview of the H2ME and Zephyr project. So you might know about this project already. They're part of a family of projects that have been funded by the FCAG in the light-duty segment, historically, starting from 2020 and still ongoing. These successive projects have progressed towards pre-commercialization level, so early TRL, to commercial deployment. And that's with projects such as HyTech, Swarm, and Hy5, and today H2ME and Zephyr. The aim of this project have been, on one hand, to increase the number of stations and vehicles deployed in Europe, and also test different mobility strategy and different type of application for this technology. So these are the flagship projects in the light-duty segment for hydrogen fuel cell vehicles and infrastructure, but they are, of course, part of a much larger rollout in Europe. Next slide, please. The H2ME projects are, in fact, 2 projects, with H2ME1 starting in 2014 and ending last year in 2020, and H2ME2 starting in 2015 and scheduled to end in 2023. There are a very large number of partners representing the full supply chain for the sector, with over 50 organizations that have committed to a budget of 117 million for this project and these activities. And this is matched by a contribution or funding from the FCHU of 67 million. Next slide. The H2ME initiative is aiming overall to deploy 1,400 fuel electric vehicles and 45 stations, hydrogen refueling stations, across 8 countries by the mid-2020s. The initiative is well underway, with today 40 stations commissioned and over 800 vehicles deployed and in operation in Europe. This will, of course, continue in 2022 to deploy the remaining vehicle. The project has tested different types of vehicles with different vehicles model and applications, 3 generations of fuel electric vehicles, and has more than tripled the number of vehicles on the road at the time. The vehicles are also testing different types of refueling solutions and strategies and feeding back to the sector. Next slide. So what has been achieved today, in addition to increasing the number of vehicles and stations in Europe, if you go on the next slide, you should be able to see a graph with an animation. The project has contributed to accumulating a very large and impressive data set that helps to validate the performance of the technology, both for vehicles and HRS alike. And this is today the largest data set that exists for this type of project. Of the vehicles collecting data for the project, we have over 80 million kilometers that have been driven and collected since 2015, and over 223 tons of hydrogen refueled. We are not going to go into too much detail today about the H2ME project, and the presentation that you will hear from Victor later will be on analysis from the Zephyr project. And the reason for this is that last year we spent quite a bit of time on the H2ME project. So if you would like to hear more about the analysis from the H2ME project, please refer to the Program Review Days presentation of last year. So now a little bit more about the Zephyr project on the next slide. The Zephyr project launched in 2017 and will end in 2022. It's a follow-up from previous projects like High5 and H2ME and aim to address the barriers that were identified in those projects for commercialization. And specifically, that means looking at the business case for fused electric vehicles that exist today in high utilization application and understanding how the HRS perform for such application. Next slide. The Zephyr project is well underway with all vehicles deployed, all 180 fused electric vehicles deployed, and most of the upgrade plan for the project completed today. That includes 60 vehicles in the UK, in London, with the Metropolitan Police and Green Tomato cars, taxi services, 160 taxis in Paris with Hype, and 60 taxis in Copenhagen with drives that were launched in the street of Copenhagen in November this year. Excitingly, across the three sites and for all of these partners, there's a much bigger appetite to increase the fleets of vehicles deployed and sort of further the deployment activities with hundreds of additional vehicles planned at the three sites. The upgrades and the station have been completed as well to ensure that in this case, there's suitable infrastructure available to support the operation. I think Victor will talk a little bit more about that and will now take you through analysis of funding on this project.
Yeah, thank you, Lisa. Yes, I'm Victor Lajona from Cenex, and I'm going to talk to you a bit about the Zephyr project. So if you go to next slide, please. And one more. There we go. So yeah, this is the basically we'll start with generically the cumulative mileage that all the vehicles have been accumulating so far. So as you can see in the graph, the bars are the cumulative mileage, and the green line is the number of vehicles deployed. So far, the vehicles have collected almost 5.8 million kilometers of data. And the number of vehicles deployed reached a peak of around 100, 120, kind of towards the beginning of 2020. But then obviously COVID happened, so that meant that the Paris operations with the step taxis had to stop altogether, and London operations were reduced by about 50%. However, the London taxis were mainly transporting key workers during the COVID pandemic, which was obviously a very nice story that we were able to tell. But as you can see in there, towards the second quarter of 2021, there's only around 40-50 vehicles deployed. However, STEP started redeploying their vehicles around July, and then more recently, around November time, Driver started deploying all their 60 taxis as well in Copenhagen in Denmark. So within the last few months, we've been collecting and analyzing more data that we will report in future presentations and reports. Next slide, please. And this is a summary basically of the hydrogen dispensed to Zephyr vehicle in a similar format. So almost 52 tons of hydrogen dispensed to Zephyr vehicles. Two most used stations are the Orly one in Paris and the Teddington one in London, mainly due to their quite convenient locations, and I will explain a bit more that in a few slides. But basically, between two of them have dispensed around 45% of all the hydrogen within the Zephyr project. And unfortunately, during the last year or so, the hydrogen dispensed hasn't been a lot, around 12 tons, so relatively low compared to the overall project. But as I said, more vehicles have been deployed in the last few months, so luckily this is starting to ramp up quite a lot. And then next slide, please. I'll go into a bit more detail now into a couple of the fleets within Zephyr. So the Green Tomato car operation of taxis in London, 50 taxis. They've accumulated around 3.8 million kilometers as of Q2 2021. They're quite highly utilized, which is kind of use case that we wanted to test within the project. So taxis covering a lot of kilometers during a year, around 44,000 kilometers per year, which is actually around 10% more than their comparative petrol, diesel, plug-in hybrid taxis that the fleet is also operating. And some of the vehicles can do, you know, a lot of mile, on average around 170 kilometers per day. But for example, one vehicle in a month did around 12,000 kilometers, which is obviously a very respectable figure and demonstrates the high use case of the taxis. And then in the next slide, what I'm going to show you is a quick animation of a day of operation of the taxis. So yeah, next slide, please. Yeah, there we go. So in this map, you will see a trace of a vehicle moving during one very long day and a few columns in there which represent the refuels. So if you click next, you will be able to, there we go. So you can see the vehicle moving basically. It's a speed trace in there. The more kind of blue it is the slower speed parts. So you can see it moving within the city center, doing a few trips in there. And then when it goes into the ring roads and the motorways, the kind of speed trace gets hotter towards the red color, which is obviously higher speed operation. And then you can see it in the evening around 7 p.m. It needs another refuel because basically this day was 539 kilometers, which is over range of a full tank of the hydrogen vehicle, which is in this case is a Toyota Mirai. And basically, you could argue that a battery electric vehicle of similar specification has a similar range, but would need definitely need a top-up charge during the day and requires between 30 minutes, 45 minutes for on a high-power charge points to get a full recharge. So obviously, in this case, in this kind of intensive case, we're testing the hydrogen vehicles provide kind of more uptime than a battery electric vehicle could provide. And then, yeah, next slide, please. I'm going to talk a bit about the step operation in Paris. As I said, the vehicles had to stop operation in March 2020 due to the pandemic. But until then, they accumulated almost 1.8 million kilometers. They're also quite heavily used, so around 39,000 kilometers per year. Luckily, they've restarted operations recently around July time, all of the 60 taxis, and we're currently collecting the data and analyzing, and that will be reported shortly. And then in the next slide, the kind of nice insight we drew from these vehicles is we had quite good data around fuel economy. So the bars in there represent the fuel economy in kilometers per kilogram of hydrogen. So the bigger this figure, the better the fuel economy is. And in the green line in there represents the average temperature in Paris, the ambient temperature. So obviously there's a clear correlation between those two figures, because fuel efficiency tends to be lower with worse with colder weather. There's a number of reasons. Batteries, fuel cells, mechanical components have typically lower efficiency with lower temperatures. You use more cabin heating, obviously, and you have kind of more wind resistance, and you've got more rain, which impacts the rolling resistance, which can all contribute to lower fuel economy. And basically, there's around a 22% difference between the colder months and the warmer months of the year in fuel economy, and it's something we have seen also with battery electric vehicles. They kind of show a similar difference between the cold and the warm months. So you could, we could conclude that battery electric vehicles and fuel electric vehicles have a similar kind of behavior or kind of difference in fuel economy between cold and warm months. Yeah, in the next slide, please. We've got the operation or the hydrogen dispensed in London and Paris. So you can see the locations of the refueling stations, and the bigger the bubble, the more hydrogen has been dispensed to Zephyr vehicles in those refueling stations. So in London, you can see the two stations that are located within the ring road and more close to the city center are preferred by drivers because of a more convenient location. The Paris stations are a bit different. It's obviously it's a smaller city, and also luckily the stations could be placed in airports, in the two main airports of the city. So drivers could use the trips to pick up and drop off passengers, also to refuel, which reduces the stem distance quite a bit. And then, in the next couple of slides, we did a simulation to understand what happens when refueling stations are highly utilized. So, so far, the stations in the project have been operating on probably a lower load that they could operate in theory. But we want to understand what the back-to-back refueling capabilities of these stations, which is defined as a refueling event that happens within 10 minutes of the previous event. So, for example, in the case we're focused on the Teddington refueling station, and around 9% of refuels at Teddington were back-to-back. And we've looked at other stations within SEPFR and H2ME projects as well. And typically, the lower the load of the station, then the lower the probability is to have back-to-back refueling, as you would expect. So we want to understand what happens with high utilization and with increased number of refuels per week. So that's why we did a simulation to understand what kind of problems that could cause. And at what point, that could become problematic for a refueling station. So in the next slide, what we have is basically a simulation of 100 Toyota Mirais during 10 weeks, refueling at a Teddington refueling station. And basically, we varied the number of refuels per day. So in the top right graph, you can see as you increase the number of refuels per day, the probability of 2 back-to-back refueling events increases significantly, and also the probability of 3 or more back-to-back refueling events. And there's a point where you reach about 70 refuels per day in this station that you start to see quite high probabilities of back-to-back refueling. So about 40% for 2 back-to-back events, and about 10% for 3 or more back-to-back events, which can be quite significant figures and could start to kind of stretch the limits of the station. And also on the top bottom right graph, what you see is the hydrogen dispensed per day. So you start reaching towards 70 refuels per day. You start getting close to the 200 kilos per day. That is the limit of the station, and it's kind of the limit of quite a few stations within these projects. And now I think Lisa is gonna give a final few conclusions on our projects. Thank you.
Thank you, Victor. Yes, so I think what we wanted also to do today is give you an insight into some of the larger conclusions that the 2 projects or the 3 projects have reached so far. And while we've advanced on the commercialization stages, it is clear that further effort is still needed to prepare for the commercial rollout for fuel cell electric vehicles and the associated hydrogen refueling infrastructure. Last year, especially, we covered a perspective on fuel cell electric vehicles and station and TCO analysis. And the finding from this shows that fuel cell electric vehicles driver and fleet operator are very high expectation in terms of reliability and performance, but also that the performance of the vehicles exceeds their expectation. That's very positive. Looking also at technological performance and expectation, it's clear that the ability to drive long range and do quick refueling, is important to make sure that the value of fuel cell electric vehicles is fully capitalized on, especially compared to other zero emission alternatives like fuel cell, like battery electric vehicles. There's clearly a need for a cluster of stations at site, especially where there are a higher number of vehicles deployed or vehicles deployed in fleet with high utilization type of applications such as taxis. And generally, we found that based on surveyed drivers and fleet operators, there's an expectation of a minimum of 2 to 4 stations being required per location. So the infrastructure that has been deployed in the H2ME and ZEPHR project and through other programs is today a good foundation to start the deployment and ensure that activity can start in Europe, But there is, of course, a need for additional sites to be deployed at strategic node and to build on existing sites in key cluster area. And there's also important aspect around planning to make sure that different stakeholder exchange and on the planning for the location of different sites and ensure that there is good reliability for these stations. At low level of utilization, the planning for the hydrogen refueling infrastructure is difficult because it is more challenging for it to be cost economic. And again, looking at where customers are based and their specific needs, to plan for the location of the stations, but also to ensure economy of scale will be key in the next year to ensure that the deployments can be cost effective. On the vehicle side, there is still a cost premium for fuel cell electric vehicles compared to diesel vehicles, but also electric vehicles. There are, however, operational advantages that shouldn't be underestimated. And under the right conditions, with the hydrogen price reducing, in particular, we are within one generation away from parity with diesel vehicles without subsidies. Finally, an important point is that in the sector, what we see, especially in the light duty segment, is that success stories are very much linked to locations or a country where there are financial incentives and tax exemption to support the deployment of zero emission vehicles. And that can be from local authorities as well as national government and European program. So that's all for us today. Thank you very much for your attention, and we'll be happy to hear if you have any questions for us.
Thank you very much, Lisa. Personally, I was amazed to see that the taxis, in fact, hydrogen taxis are more used than conventional diesel taxis in London, 10% more. That's clearly an achievement there. I would like to remind the audience that feel free to ask any questions if you would like to get details on this project. Now is the time to do it. First, general question to you, Lisa. You said that there was feedback from the fleet managers and the drivers about the vehicles, that they like performance and reliability. But what about the customers? What is their feeling about these hydrogen vehicles?
Yes, and I think we have to say that for the taxis, especially, we don't necessarily have a formal way to survey them through the project, but we do have anecdotal evidence that the taxi driver report back to the project. And it's very interesting to see that they are very keen to use those taxis. They're very excited to learn about the technology. And taxis are really an excellent method really to a good champion for the technology.
Thank you. A question from the audience, which is the following. H2ME, H2ME2 started sometimes 4 or 5 years ago. And in that same period of time, the battery cost has decreased. Are the same business model or the cases from 4 years ago still applicable for fuel cell vehicles? Should this business model be revisited?
Of course, yes, it is a very fluid environment. In the sense, the sector for zero emission vehicles is evolving. And it's good news that we see, on one hand, battery electric vehicles progressing and advancing, because it does mean that overall we are closer to decarbonizing that sector. The business case for light duty fuel cell electric vehicles is evolving, is still very relevant, especially in this high utilization application, where the benefit of long range and quick refueling is very important. If you are a member of the police, you will need to be able to be sure that at any point you're able to take one of the vehicles from your fleet to go on intervention and emergency response. You cannot afford to wonder whether your vehicle will be in the process of recharging a battery over a certain amount of time. Similarly, for taxi operation, you want to be able to take a course that will take you very far away without having a concern of having to stop on the way for a relatively long recharge. So if you want to drive from Paris to Brussels, you want to be able to take that course. It's a very good course. I need to be able to do it. So I guess what I'm trying to say is that to make sure that overall the transport sector in the light duty segment, but also in other segments, is able to decarbonize, we need able to have solutions that work for all type of application, not only for individual drivers, but also for fleet operator. Otherwise, we might be in a position in a few years' time where we hit a wall and don't have an option to decarbonize some of the segments and some of the application.
Thank you very much, Lisa. Now it's time to move for the hydrogen buses. And for that, we'll have a combined presentation of project JIVE, JIVE2, and Merlin. JIVE and JIVE2 are supported by the FCH and Merlin by Connecting Europe Facility, CEF. This is to say that there are synergies between both programs on hydrogen. So I would like to introduce Madeleine Ojakovo from Element Energy, coordinator of the project, and Dr. Stefan Hecker from Sfera, who will highlight the early data collected from JIVE, JIVE2, and Merlin. Madeleine, the floor is yours. Thank you.
Brilliant. Thank you very much, Lionel. It's a pleasure to be speaking to everyone this morning about the family of 3 projects, commonly known under the umbrella of JIVE. So if we could have the project overview slide up, please. Brilliant. Next slide, please. So firstly, I'd like to give you a little bit of background about the 3 projects. As Lionel mentioned, there are synergies between the 3 projects. So Merlin, JIVE and JIVE2 are supported by 62 million euros of funding majority from the FCHJU, but also from SINEA for Merlin for the infrastructure. And this is leveraged by, this leverages private and national co-financing throughout Europe to deploy the vehicles and get up to that 200 million plus project budget overall. So starting with Merlin, or its full name, Models for Economic Hydrogen Refueling Infrastructure. This is the SINEA funded project and was the first of the project concepts, which is looking at deploying 7 hydrogen refueling stations and how to make those stations economically viable. The project is currently entering its final year and all the HRS are expected to be fully commissioned by February 2022. So the core concept of this project was to identify the anchor demand which can support the hydrogen refueling stations year-round at a sufficiently high load. So this is where JIVE and JIVE2 come in, and they provide that core anchor demand for the stations. JIVE and JIVE2 are together the flagship bus project for fuel cell buses in Europe, and previous generations of fuel cell bus projects over the last 20 years have proved that the technology works, and JIVE and JIVE2 really are providing that pathway through to scaling it up and that pre-commercial stage. Next slide, please. So looking at the overall objectives across the 3 projects, we'll deploy 310 fuel cell buses across 17 different cities and regions within Europe. This is validating large-scale fleets of fuel cell buses. So within the JIVE projects, we're deploying fleets of between 5 and 50 buses, really looking at that range of fleet sizes. And we're also focusing on building expertise throughout Europe through dedicated training and dissemination activities. Next slide, please. So where are we to date? So by the end of this month, we're expecting to have 190 of the vehicles in full operation, which represents 62% of the project total. And all of the 310 buses will be under contract. We have buses which have been deployed in the project from 6 different European suppliers in single deck 10.5 and 12 meter models, articulated 18 meter vehicles, and also double decker models primarily in the UK. The bus operators are also basing the deployment on longer operational lifetimes of the vehicles. So everyone in the project will be operating the buses longer than the lifetime of the project, between 8 and 15 years. And this brings the fuel cell bus technology into line with standard vehicle concession periods across Europe, which is similar to other drivetrains and diesel drivetrains. So overall, the buses are performing more or less as expected, with a few teething issues which are expected during the early stages of a project, and Stefan will talk about that a bit later. So the next key progress point I wanted to highlight on the following slide around the HRS deployment. So looking at the total numbers, by the end of this year, we'll have 9 of the stations out of 17 fully operational, with the rest to follow by the end of next year. We have 4 of the stations currently in the commissioning phase and should shortly be in operation in the first quarter of next year. The remaining 4 are at the civil works and permitting stage and will follow in 2022. We have 15 different suppliers providing the HRS equipment or the hydrogen supply, which is really encouraging as it's demonstrating a healthy competition within the market. One of the key learnings, I think, really around the JIVE projects has been to sort of ensure that the procurement and manufacture of buses and infrastructure is aligned and done in parallel, but it is a tricky balance to strike. So several of the operators where buses have arrived slightly in advance of the refueling stations being ready have been successfully trialing some mobile HRS as temporary solutions to service the buses. Please could I have the next slide? The final point that I want to highlight today is around the progress on the price. So those of you familiar with the JIVE projects may have seen the graph on the left before. The central objectives of the JIVE and JIVE 2 project are to bring down the cost of vehicles below 650,000 euros per bus and 625,000 euros per bus, respectively. On the left, we can see that JIVE has successfully brought down these prices when compared to the previous generations of bus projects. We start the graph with the Chic project in 2009, where the prices for buses were over 1.5 million euros. On the right of the screen, you can see the actual capital costs for the JIVE buses ordered in different years of the project, starting at 2018. The minimum is in orange, the average is in blue, and the maximum is in grey. So what you can see is that JIVE has successfully sort of capped the maximum price of the basic specification bus at the 650,000 euro level. Not only this, it has exceeded both the 2020 and the 2023 FCHJE multi-annual work plan targets on price. We're now consistently seeing buses below the 500,000 euro mark on the minimum level. In 2018, when we had our first orders, this sort of minimum price was only accessible for very large orders of over 30 buses to have that below 500,000 euro price. We're now seeing that same price is accessible for orders of only 10 vehicles, which is extremely encouraging, seeing the technology becoming more commercially viable, although we're still quite far off the battery electric prices. On the final one of my slides before I hand over to Stefan, I wanted to highlight a couple of the key lessons learned. If I could have the next slide, please. Thank you. JIVE has proved that the technology it works at scale. We have used sort of multiple funding sources, which have added some complexity to the project implementation, but these are still necessary to have funding for the business case for fuel cell buses to work. New financing models are emerging, which is making it less reliant on the funding and financing from the public sector. And new private sector leasing models, for instance, are reducing the risk to operators and building confidence in the technology deployment over a longer period of time, for that 8 to 15 years. There is also still work to be done on developing post-Jive deployment pathways. Now that we're reaching the point where all the buses are ordered and mostly deployed, new funding sources for the next generation of buses is necessary and under development. Also, development of new options, coaches, minibuses, and more diversity across suppliers are emerging and expected to emerge in the next couple of years. There is also still work to do to collect and standardize the data from the bus suppliers. Greater transparency from the OEMs on the performance of the bus is a vital factor in continuing to build that operator confidence in technology. The final point I want to share is around continuing to share the best practices with operators. We, within the Jive projects, have built up a lot of knowledge and expertise over the last 4 years of the project's lifetime, and will continue to share this through dedicated training with operators and cities not yet familiar with the technology, and hopefully we'll see that increased deployments in Europe in the coming years. I'm now going to hand over to Stefan for a closer look at the results and performance data.
Sorry, now thank you, Madeleine. I hope you can hear me. And if you just put up, yes, the first slide. So I will talk a bit about the performance of the buses so far that we encounter in the Jive project. So just the next slide, please. Yes, here just the number of buses currently in operation is indicated. You see the uptake beginning from January 2020 up to now. Now we have over 120 buses at 7 different sites. So the first, just to go a bit through or to mention them, is Bolzano, and there we have still buses from the SCHIC project running that we also have in our evaluation, but they are quite old now and they are really at the end of their lifetime. As you see at the beginning, there were 5 buses still, and now there are only 3 left. But now new Solaris buses are put into operation. With Cologne, we have the largest Van Hool bus fleet. They started with 5 buses in January 20, and now they have already 35 vehicles, and they will still get several Solaris buses in the upcoming months. Wuppertal is a bit lower in numbers, but a bit similar. So they all also deploy Van Hool and Solaris buses. Then with Po, also the first Jive 2 site came into the operation with in total 8 Van Hool buses, 18-meter buses. So only 5 of these are Jive buses. The 3 others are from 3Emotion, but we consider them all in our evaluation. Aberdeen, the first British site with 15 double-deckers, and then London following just after that with 20 Wrightbus double-deckers. And finally Groningen since July 21 with 20 buses. Unfortunately, we have no data from Groningen yet. But I think, yeah, from that side, the data is still being processed and just also the qualitative assessment is made. Next slide, please. So I just want to point up some, let's say, KPI values, and it has to be said that a period of 6 months is not long, although it seems long. So there is still, let's say, the whole operation of the buses is not yet really fixed. There are still teething problems, etc., that we can clearly see, or that is clearly reflected in the diagram. We have one top site, that's the blue one on the top right. that has from the start a very high mileage. So here's just the monthly distance driven indicated, as there is a target at about, can't read that, I think it was 3,800 kilometers per month, and 3,667 to be exactly. That's from the yearly mileage, just broken down. For other PTOs, like public transport operators, like number 6, we have a continuous ramp up. So that is clearly related to some problems in the start, to some teething issues. Especially for operator number 4, there were quite immense teething problems, and then they had also a flooding issue in last summer. So that was really a bit of a problem there to get the buses running. But now the numbers are increasing, and others are not really at the do not really reach the KPI, but they have a quite high level of their operation. And also for the last 2 dots at the very right, they just started. So you can't say really anything about that value. So it's quite low, but they, as I said, they just started, and their teething issues are really normal. So as a result, most sites do not reach the target. What is on the one hand really related to very normal teething problems, but on the other, most sites that started in 2020 were highly impacted by some lockdown measures due to the COVID pandemic. So on average, there's a quite positive trend, and we hope to see the target being met in the next months. Next slide, please. What is very, very good from the beginning, in contrast, is the hydrogen consumption. And in total, we have a really low consumption on average with 8.05 kilogram hydrogen per 100 kilometer as an average. And we see that most sites do not have any problem to meet this target. And even the operator, I think it's 6, that started quite high, continually dropped the consumption and now is far below the value, the target. So the target is at 9 kilograms for the solo buses. And you have to say, this is really a bit special, I think, that also the 18-meter buses and the double deckers does not have any problem to meet the target, even for the solo buses. For some sites, it's not really clear for all sites, but for some of them, we see, for example, for PTO 4 and 7, we see the same seasonal fluctuations as we have seen for the taxis. So there's a consumption increase in winter. What we also see is that for these 2 sites, we have the same bus model, but quite some difference in consumption, what we will have further to investigate. So, yeah, I think I said everything. Next slide. So here's a bit, let's say, chaotic picture that's representing the fuel cell hours. Also, this is a KPI for the project, and the a bit low numbers are correlated certainly to the limited distance driven, as we have seen. And but mostly we have some, let's say, increase despite the purple operator. For the others, there's an increase and quite some positive trend. We have also the problem that it seems to be some difficulty for some sites to measure that data point, though this is quite a challenge that we will have still to overcome. We try to circumvent some transmission problems also by extrapolation of values that we have. So finally, yeah, there's a slightly positive trend. 2 sites already meet the target, but yeah, really, that's still the beginning phase, the first year, and we will see how that continues. We are quite positive that this will also stabilize or increase and then stabilize on a far higher value than we see now. Next slide, please. So this is the about the reliability of the vehicles, that a measure mean distance between failures, so just indicating how many kilometers are made between two failures. We have here data from 3 sites. So, but we have to say that we measure the downtime, so that's just 100% availability would be 24 hours on 7 days. So we see how many hours a bus is not in operation due to any form of downtime. We also see here that various sites face some difficulties to report the downtime according to the criteria we use. That's the trust criteria. And the target here is 2,500 kilometers. That's not really met here, but the rather low current values we see here is due to the fact that one operator, so Bolzano, as I said, operates, so one color here stands for the former Schick buses, so they are quite old, and it's quite clear that they are not as reliable as a new bus. And the others also already I mentioned that they experience still quite some teething issues, so we are quite confident that these KPI will also be met in the future. It also has to be said, when you only have a very small fleet number, then the failure of one bus has an extreme impact on this KPI. So it's not a very stable value, and we will see how we can deal with that topic. But I think that maybe it's also no problem any longer when the fleet sizes become larger. And my last slide is about the downtime reasons. That's the wrong header. I think that should be, that should read performance evaluation and downtime reasons and not fuel cell hours. So that's for the 3 sites a bit the breakdown of reasons why they fail. And we see for the left side PDO2, the main reason are fuel cell stack issues as a main cause, with almost 40% of downtime. 3 and 4, they have electrical components as the main issues, but we have a quite different share of that downtime reason. And yes, as a final, it's a bit difficult to say up to now with the limited data we have, and also that not all bus operators report all downtime categories. There are some differences in the internal systems and processes they use to take that value. So the downtime duration and also the associated reason may vary between the different sites. So that is a very preliminary result and should be taken a bit with care. But I think that is very, very interesting to see for the operators, and also between different OEMs and sites. So where are the biggest problems still for the fuel cell buses? And I'm very excited to see how in the future that will develop. And I think that was it from my side. Thank you very much. And I think, oh no, I have a summary, sorry. Yeah, so we see that more and more sites become operational, and we expect in the upcoming months a high increase in new sites and also data. So that will be some exciting months. We also have the, let's say it's good to have further different OEMs, buses from different OEMs that we can compare, where we see differences in performance, etc. Unfortunately, the current values have been highly impacted by teething phase still from every side, and additionally the COVID pandemic. And we hope that this will be better, let's say, all the value that the buses can drive longer, that there are no longer any breakdowns, etc. And also that the technical problems of the beginning will decline. So there's a positive trend. What is an ongoing task is data availability and the harmonization, as we have different operators, as we have different OEMs in our evaluation. But we really expect further insights from the long-term evaluation, and that as we get more data from more sites. Okay, now it's up to you again, Lionel.
Thank you very much, Madeleine. Thank you very much, Stefan. A question for Stefan. You have highlighted so far technological data, performances on the buses mainly. If I was a PTO interested into the hydrogen buses, perhaps I will be looking or interested by economic data, for example, total cost of ownership or the environmental benefit of the hydrogen bus solutions. Will you consider collecting and analyzing both TCO and environmental benefits in the framework of JIVE and JIVE 2?
Yes, that's a task for next year. We have on the agenda, and that will be done based on the real data that we get from the operators, and we will do that exemplarily for some cities that have also running electric buses and diesel buses, and there we will make a comparison on the one hand from the environmental performance and also from the TCO.
Thank you. So that means we'll have fresh on-the-field data between real hydrogen buses and real diesel or battery buses in operation in different cities in Europe. That's clearly important. Now, a question for you, Madeleine. You have presented the different sites, but can you explain to us where it was the fastest to move from the idea, from the concept, up until the materialization, where we do have the buses and the HRS in operation? Why it went faster in some cities than in some others? What are the key factors?
Yeah, I think there are a few key factors there, Lionel, actually. I think firstly, sites who had previous experience from previous generations of buses like Aberdeen in the UK and Cologne in Germany were able to move a lot faster due to their previous experience with operating buses and procuring fuel cell buses. Secondly, there is actually a point around time. So those cities who joined at the start of the project and were the early trailblazers within JIVE took a little bit longer to get orders. So this from order to deployment. So that could be due to OEMs developing their first ever fuel cell buses, or the first of the new generation of buses. And that manufacturing process takes a bit of time. So we were seeing between 12 and 24 months between order and delivery and deployment of the buses to start with. For more recent orders in 2020, 2021, we've seen as little as 6 months between placing the order and actually getting your first bus delivered. So the sector more broadly and the OEMs are increasing the speed at which they're producing the buses as well. And we're seeing that the lessons shared between operators within the project is having a positive impact. So cities like Cologne and Aberdeen were able to share their lessons learned with recent orders, such as in Barcelona, where it was quite a quick process. So it's really encouraging to see that improvement overall in the sector.
Thank you very much. Now we'll move towards trucks, and not only, because Corridor H2 Occitanie is a project about hydrogen trucks, refrigeration units, and coaches. And to introduce to this audience this project, Mr. Raphael Schongen from Hydrogen Advisors will explain what Corridor H2 Occitanie is about. Raphaël, the floor is yours.
Thank you, Sebastian. It's a pleasure to be with all of you today. And if you could put the slides on, I will give you a first overview of what is Corridor H2. So initially, this project, as you have mentioned, Sebastian, has been kickstarted by the Occitanie region. It is now a project that has more, in terms of budget, that exceeds 100 million. But you need to notice that it is a first part of a larger chain of ecosystem that will span, and I will show you slides afterwards, from the Iberian Peninsula up to Benelux and beyond. We started it because it's the Occitanie region that launched it, and because the supporting entity that are the European Investment Bank and the European Commission, and you see here quite a bit of money that they have put on the table, a total of close to 60 million, mentioned that it's great to set up a corridor along the TEN-T corridor, that the two TEN-T corridors that are behind, but we should start with one region. You also see, and I will show you in the next slides, that in the Occitanie region, please stay on the first one, and then I'll move faster on the other one. You have already a very well-established hydrogen backing from public authorities with a dedicated development agency, the one in red, the ADOC, a dedicated energy agency, which is involved in terms of capital equity into projects, the AREC, and you have also a dedicated hydrogen agency or unit called IDO. And who are we? So you mentioned I'm running Hydrogen Advisors, but on this project I've worked together with SEIA Consulting and Element Energy, that are other advisory specialized in hydrogen, and our work was to help construct and develop these projects. So without further ado, I move to the next slides. We will show you that hydrogen is not a new topic in Occitanie region. It has been there since already more than 10 years, a decade. They have developed an array of different projects, not only hydrogen station, renewable capacities, trucks, buses, cars, hydrogen refueling station. They also worked on trains. They are producing part of the hydrogen trains. They are working on harbors with the PORFSET, and they're also working on hydrogen airports with the project iPort around Toulouse Airport, where you also know that there is an ecosystem around Airbus with the future hydrogen plane. So it's a very active region, and it is also a region that 2 years ago decided to table 150 million euro fully to hydrogen, with a hydrogen plan and strategy. And up to now, I do believe that they are, in the top 3 to 5 in terms of funding on one single region in Europe, fully dedicated to hydrogen. And that came a little bit ahead, and then at the same time as the European plans and the national plans that we have seen. So moving to next slide. Why did we suddenly engage as consultants with the region? Is that despite this plan, and despite also a very, very intense renewable energy plan in the region, they still face today, but they want to tackle that issue, a very intense traffic of heavy-duty vehicles passing in front of their doors on the edge of the Mediterranean Sea. But you need to know that next to this highway on the TEN-T corridor, you have, protected areas for Natura 2000 areas. And you also have an array of beaches where the regions every year attract tourists and windsurfers. And so they want to tackle this environmental issue related to fossil-based fuels vehicles, because in total it's 30 million a year and 9 million trucks. So that's how we came in, following a call for tender. And we basically said, well, we should focus on end customers, transporter and chargers. We should bring along the table all the suppliers of trucks, potentially coaches also, because you are going to develop around your refueling station also local users. And we also noticed that in Perpignan, in the south, in this red zone, you have a very big platform, logistic platform, where fruits and veggies coming from the Iberian Peninsula come refrigerated, and then in the past used to be put on a train going to Rungis, which is another big refrigerated logistic platform south of Paris, and now are going by truck up north. So that's why, how you said, Sébastien, came into the frame, not only trucks, but also refrigerated units and coaches. Let's move to the next slide. So who is involved? So the target here was directly to think about a corridor that is spanning across regions, focusing on the end customers with those 3 target applications. It is not only about Occitanie region, and the president of Occitanie region has written to the president of different other regions along the corridor and received support on this vision. And the funding strategy is, it does not appear in the first slides because the Occitanie region is free to allocate the amount it wants, but its involvement is in tens of millions next to the funding of the EIB and the European Commission via the CEF fund. Next slide, please. So as I said, you have one now anchoring region, which is Occitanie. It's quite likely that the next region to move on will be Wallonia. Grand Est has showed also very much interest. They have tabled their hydrogen strategy. Last year, the same consortium of consultants were involved in supporting that strategy, and a corridor H2 or heavy-duty trucks development is part of it. We have also interest from the Catalonia region, so we will see further development regarding this project in other regions, but I will focus the next minutes my talk on what has happened in Occitanie, because this is the model and this is happening right now, and it's quite nice to see how it's developing. Next slide, please. So we brought, it's basically a work that took 2 years, but we have now money from the European Commission and the EIB that needs to be used by 2023. So we need to be quick with implementing the solutions. We brought around the table, you see 4 types of players. On the upper part, you see regions and clusters. So it's not only about, you know, the political arm, it's also about the logistic clusters or their energy clusters. It is then on the left-hand side, the solution providers, and this via the involvement that we have had as consultants in an array of different projects and also on a daily basis with suppliers of solution, we managed to get the interest of usually either the CEO or Mr. and Mrs. Hydrogen inside any of the company that you see on the left-hand side. So you have an array of different suppliers, not only of trucks, but also of buses, I will not detail all the name, or companies that are developing hydrogen refrigerated solutions. Many of these names are familiar to our hydrogen community. Then on the bottom of the slide, you see all kinds of different suppliers of energy, big and smaller ones, many entrepreneurs. And on the right-hand side, the actors without which this project would not fly. It is absolutely key, and we started from day one focusing on the end customer. There is no project, there's no corridor if you do not have the end customer, and if they do not feel confident and they are not helped to embark on a journey using hydrogen vehicles. So that was a center focal point since day one. And here you see different names. I mean, today hydrogen Europe is operating out of Brussels. So Colruyt is a big, you know, supermarket chain, but you have Steph, which is a company that is specialized in refrigerated transports. I just took 2 of the first names that are popping there. You see Ninatrans, this is the company of the president of the Transport Association in Belgium. I will not detail further, but just to say, it is absolutely key to embark these people. The other key message I'll send you is here, this project is completely open to anybody. Any supplier of trucks, of vehicles, or refrigerated solution coaches, any supplier of green electrons or green hydrogen, any transporter or charger. It's completely open, it's financed by public financing, and this is a model that is now intended to be replicated. You have some other corridors or local ecosystem with hydrogen vehicles that are usually developed by a limited number of partners with public funding, But the essence is that they came together and they pay for the development cost, and then they get EU or local funding. Okay, this one here is anybody is allowed to come, and then they go through a process to be approved to get public funding. But it's super, super open. It's not proprietary. It's not in the hands of a few large companies or given players. Now let's move to the next slide. And what you see in the market, there are a lot of solutions up there and flying, from, carriers to tractors to special vehicles to also refrigerated trails. So we are not out of options. The limitation that we have is out of all this, not all are able to be implemented in TENS in the 2 coming years. So if we move now to the next slide, you will see what is actually this first amazing break that Occitania region has managed with all its teams and ecosystem to put on the table, and for which there is this public money from Europe. So the entire project is, as you can see, is about close to 100 end use, where you have 15 coaches, because we considered it would be interesting to also support coaches from city to city. And you have 40 trucks, 40 refrigerated trailers, and then also 20 refrigerated units so they can do a retrofit. Then there are 8 stations planned, 2 that are large, 6 of 600, and then 2 that are at 900 to 1 ton or both. And from there, the total budget on the right-hand side is derived, and you see that is over close to 110 million. And then the support. Everything goes through the hands, all the public money goes through the hands of the Occitania region, which makes it much easier because you don't need to go through an approval of every single player of the project, which is usually what happens when you get a consortium and get it approved at European level to get funding. Okay, so that is why the role of the Occitania region here and potentially in other regions of a public entity is absolutely key. Okay, in terms of structuring, allocating the funding, taking eventually equity in projects. So where do we stand on this project right now? I suggest we move to the next slide. Is we actually, as I told you, started this project close to 2 years ago. It took a lot of time to structure it, think it through, discuss with the different people, okay, what is important, what is less, and then to get the funding. And we got a lot of support and an interest and positive support and advices from the EIB and the European Commission. And we ended up starting really implementing it this year with 2 calls. 2 calls, a first call, so it was in spring, as you can see on this slide, 2 calls. A first one, which is, please, companies that want to produce, transport, and distribute in refilling station hydrogen, raise your hand and come up with very concrete, detailed projects in which you need to provide hydrogen at a maximum of €9 per kilo and a trajectory taking it down to €7 per kilo. Then we, and that means a group, a selection team, will stamp the projects that will be selected and funded, and you will see that this job has been done. It will show up in the next slide. Then we started another call, but this is not a call for project, it's a call for interest. And this one is towards transporters and chargers. Please raise your hand if you are interested in acquiring one or several hydrogen vehicles, either refrigerated trailer or trucks, and then we have separate work for coaches. And that is still ongoing. Okay, so you have seen that here on this slide that we started then in June a dedicated task force which was to support transporters and chargers in understanding hydrogen and applying to the second call for interest. The call for project was much easier because you have a lot of people who are already active in producing hydrogen and distributing it. In September, then we did a one-day event to show what hydrogen trucks are, and I'll show you some pictures. In November, we published the results for the hydrogen production sites and transport solution and hydrogen refueling station. And now in December, we will receive, the region will receive, and the selection committee will receive the first batch. There will be a second batch later of chargers and transporters asking for financial support to acquire vehicle. So next slide, please. So this is the result of the approved production and distribution sites. You see a map where you have fundamentally two, it's blue, you can't really see well, but you have basically two production sites, one up in the mountains and one on the seaside next to a harbor. And you have a series of refueling stations that are along the TEN-T corridors. And you see also a little dotted line between two cities. This is where you're going to have coaches running from one city to another one. So it was a competitive process. Everybody was free to table. And then there was a selection committee chaired by the region to decide on which project. Like it always happens when you have public funding. It's just the best student in the class or the best project for the community that gets stamped. And this is the result. Next slide, please. So, you know, lots of people, they don't know actually what is a hydrogen truck. They are very, you know, aware of what a diesel truck is. They have had, you know, sometimes in their hands an LNG truck. So they are extremely interested to understand, but there is nothing better than just showing hydrogen trucks. So we told to all the companies that are producing hydrogen trucks and following the project very closely, I've showed you the list. You are free to come. We have in the Occitanie region one of the very few testing rings for trucks in Europe. Okay, come and we'll organize an event where you can show trucks. And we also managed to organize or to invite the France Supply Chain Association, so the association of all the big brands and smaller brands of transporters and company charging these transporters, to come and have their congress the same day on the circuit. And everybody was there, so local players and national players, to see trucks. And we ended up inviting Hyundai and Aisin Motors, because out of all the companies, those were the only two who told us, oh, your project runs now from 2021 to 2023. Many said, well, we cannot provide you many trucks. By then, we're still prototyping, or at prototype stage in different pilot projects. We are not going to be able to sell up to 40 trucks. It's only Hyundai and Aisin Motors who say we can. So they were both invited. Hyundai didn't manage in the end to bring a truck for custom issues, and so Aisin Motors came all the way down, pulling in a truck, and this is the one you see, and it was a major success. You cannot imagine, I mean, many of you are in the hydrogen economy, but that was, major press attention, major from the customers' attention, everybody wanted to see and touch. And that helps a lot now in the work that we are doing to further teach, so to say, hydrogen potential users, hydrogen trucks potential buyers and users about what is hydrogen and how to develop, okay? And they can get funding between the delta of cost, a diesel truck is about 100K, hydrogen truck up to 600K. So you have a delta of 500. And depending on the size of the company, you are somewhere with all these fundings that we have gathered between potentially 60 to 80% of funding, okay? Because you have some special regimes in France, environmental regime, fiscal regime that help you increase eligibility level. So this is just to tell you where we stand. We look forward to receiving now their proposals for funding and to move next year into implementation. And of course, relying on all those who want to provide vehicles. Next slide, please. So this ends my presentation. You have here my contact details. And if there is any interest from our hydrogen European community at large to have further explanation, please do not hesitate to reach out to us. As I said, major milestone now in Occitanie happening. People can come, see, and touch. Without the political momentum from the region, this would not happen. But from day one, the wish of Occitanie region is to see it replicated in other regions, and we are ready to help other people think that through. Thanks for the
Thank you.
opportunity to engage with you today.
Thank you very much, Raphael, for your presentation. A very short question, perhaps my personal curiosity. I've seen today the plan is for 40 trucks, the 15 coaches, and as well 40 refrigerated trailer. Why is that? Is there a specific need for refrigerated trailer in Occitanie, or is there a sector which is better suited to switch to hydrogen?
It's a very good question that you asked, Sebastian. Actually, what we realized is that whereas you have got, Euro 4, Euro 5, Euro 6 rules regarding trucks, you do not have anything regarding refrigerated trailers. And a lot of the traffic that I've referred to is basically trucks coming from the Iberian Peninsula and bringing up north all the fantastic veggies and fruits that we will see on our tables in the northern part of Europe. When you go to the supermarket, they come from there, and they are not coming, in non-refrigerated trucks. They come in refrigerated trucks. And the refrigerated trucks can run on gasoline, diesel without any emission control. That's where we stand today. And when you refill a hydrogen truck, it's super easy to refill, the trailer behind. And once you do it, you are set to go, it doesn't consume that much a Frigo box. Okay, so you are set to go for a couple of days. Okay, and so you can even leave your, refrigerator trailer on a parking and logistic zone until somebody picks it up. And so it's a very nice additional combination. It increases the quantities. And that came into the radar of the project team, because you have this logistic platform within the Occitanie region in Perpignan, where a lot of trucks currently stop. And also because in France and in the region, you have an offer. The first hydrogen refrigerated trailer has been put on the road by Chero, which is a market leader in refrigerated trailers in Europe. And you also have Bosch that is also working on that with a factory that is producing part of the parts in the Occitanie region. So those are two other elements, to take into account. But first and foremost, it would be, if you want to decarbonize completely this traffic, fruits and veggies, you need to think also about the trailer next to the Polar. So I do believe I answered to your question, but it's a very good question.
Thank you very much, Raphael. Indeed, you answered the question very nicely, and now it's clear for me why the refrigerated trailer. We are reaching the end of this session. So on behalf of our online audience, I would like to congratulate all of you, Lisa, Victor, Madeleine, Stefan, and Raphael. Continue the good work on this transport demo project so that we get more and more buses, cars, and trucks visible on European road to decarbonize them. Thank you very much, and enjoy the rest of the day. Bye-bye. Ladies, gentlemen, good afternoon. Welcome to this session about heavy-duty transport. We will have the pleasure to listen to the outcome, the results, stemming from 4 different projects. We'll go on the road, in the air, and on the sea, meaning we'll speak about hydrogen trucks, hydrogen aircraft, and ammonia in that time, for ships. I would like to remind the audience that you can ask questions through the platform. There is a dedicated item, a button, open questions. Please just type it, and then I will verbalize it to the speakers. So each speaker will speak about its project, then it will be followed by a small session of questions. Without any further comments, let's start with project H2Hall about trucks. This will be presented by Mr. Andrew Flagg from Element Energy, together with Giovanni Gianelli from H2 Energy. Andrew, the floor is yours. Andrew, perhaps you are still unmuted. We cannot hear you at the moment, unfortunately.
Okay, are you able to hear me now?
Yes, it works. Thank you.
Sorry about that. Small technical issue, but yeah, thank you very much, Lionel, for the introduction. Good afternoon, everyone. Today, I will be giving a very short introduction to the H2Hall project before handing over to Giovanni Gianelli from H2 Energy to give a bit more detail on the Swiss activities within the project. So if you could show the slides, please. So H2Hall is a project funded by the FCH-JU starting in 2019 and is receiving 12 million euros of funding contribution from the FCH-JU. H2Hall is the flagship heavy-duty hydrogen fuel cell truck project in Europe, developing and demonstrating the technology. As you can see on the bottom of the slide, there's a whole host of project partners involved in the project, with truck manufacturers, fuel cell suppliers, HRS deployment partners, as well as industry experts carrying out the cross-cutting activities. If you go to the next slide, please. So in a bit more detail, H2Hall aims to develop and deploy 16 zero-emission fuel cell trucks at 4 sites across Europe. The vast majority of these trucks will be 44 tons in gross combined weight. And in addition to this, new high-capacity hydrogen refueling stations will be installed to provide reliable, low-carbon hydrogen supplies to those trucks. Generally, the project aims to deploy heavy-duty trucks that meet a variety of operating requirements to prove the viability, the reliability, and the safety of 3 types of trucks for use in European long-haul logistics operations. H2Hall aims to develop the business case for the further deployment of heavy-duty fuel cell trucks, preparing the European market for the further rollout of the technology. And overall, the H2Hall project aims to catalyze further action from the sector, providing a platform to build on and scale up from. If you go to the next slide again. So in terms of the delivery phases on H2Hall, it's not quite as structured as it is on the slide here, tend to overlap a little bit more. But generally, the work in the project has started with the design of the fuel cell trucks and the development of truck specifications, technical specifications, as well as the preparation activities at each of the hydrogen refueling station sites for truck deployment. As the trucks are developed, they will then be tested in real-life operations, and data will be subsequently collected from these operations throughout the project. Each truck is planning to travel more than 1 million kilometers during normal commercial operations. And the data and results from these operations will be then analysed. It will be collected and analysed with key conclusions, lessons learnt, and best practice disseminated to promote the future development of the industry and then scale up the technology. On the next slide, there's a short overview of some of the the key progress in the project to date. So since the start of the project in 2019, the partners have worked in various different aspects to develop the technologies. So there's been major progress from the truck manufacturers, Iveco and VDL, who've progressed with the activities to design the trucks, setting out the technical specifications with the fuel cell suppliers as per the requirements of the different refueling station partners at each site. Prototype trucks have been developed with functional fuel cell samples, and these are currently being tested. And in parallel, the actual H2 trucks that will be deployed on the road are in development and construction, with deployment of the vehicles to the 4 sites to commence from 2022, so from next year. And you can see on the slide at the top in orange is some of the designs for the VDL trucks being deployed, and underneath that is some pictures from the Iveco Nikola manufacturing facility where the H2 trucks will be constructed. And if you then go on to the next slide. So this is on the HRS, the refueling station side of things. So the partners for the refueling stations have focused so far on the site preparation activities. So that's involved, for example, the station designs, permitting, securing the hydrogen demand, and now moving on to activities with the civil works and installation activities. In addition to this, as part of the preparation activities for the sites, H2 partners have also been supporting other projects within the industry, for example, supporting work to develop heavy-duty refueling protocols. And there are several project partners that are very engaged with the FCHJU-funded PRIDE project, which shows the synergies and the collaborations between different European projects to deploy the industry and to develop the industry. 2 refueling stations in Switzerland are already operational. I'll let Giovanni speak some more about that. And the H2 funded site in Rothenburg in Switzerland opened at the start of this year. The remaining H2 stations will be commissioned in 2022, aligning with the delivery of the H2 trucks, so from next year. Overall, we've got a very exciting year ahead in H2 as we start to get the first trucks on the road and the hydrogen refueling stations commissioned in the project. So over the next couple of years, it's going to be a really exciting time to share some of the emerging results, lessons learned as we start to collect data and some conclusions from the project in the coming years. I'll now hand over to Giovanni to go into a bit more detail on the Swiss activities within H2.
Thanks, Andrew. If we can move to the next slide. So this is the situation that we see currently in Switzerland in terms of how many Swiss HRS are connected, are already active. The one that we will be discussing more detail today is the one that is in red, the Rothenburg one. That is the one that has been connected to the H2 project. Andrew mentioned 2, but in fact we have 8 already running hydrogen refilling station in Switzerland. The 2 most relevant are in any case the Rothenburg one and the Hunzerswil, the one that you saw in the middle of the page, in the middle of Switzerland, with the link to the COP distribution center logo. This is important to say because Iveco is now entering into an agreement with COP for the distribution. So the 2 trucks, the 2 rigid trucks that we will receive December 2022 will be most likely serving the service with for COP for goods delivery. The Rothenburg station has been used at the same time because in the other side of the road where the HRS is situated, there is an existing Iveco service center that has been upgraded, let's say, to also maintain and service hydrogen trucks. And so for this reason, we have seen that this center, this HRS, could have benefits for the integration into the H2All program. So if you go to the next slide. This is a plan for the activities that has been carried out for the execution of the plant. Basically, we started in 2019 and the first quarter of 2020, where we can say that the front end engineering has been done, plus the first contact with the authorities for the deployment of the documentation for the permitting. And then we entered into the real permitting phase and real execution of the project with the selection of supplier in the second quarter of 2020, to then progress in the course of the 2020 on all the activities for purchasing, installation, and commissioning of the station. That has been concluded by the end of January of this year with the inauguration, the formal inauguration of the HRS. This to say that basically in the course of the 2020, the lead time from the identification of the station until the completion of the engineering, detailed engineering, and selection of suppliers and civil works and installation, the work has been done in 12 months, roughly. Since January 28, we are in operation also with the Rothenburg station, and this is the station that we use also to gather the data and collect the data in the frame of the H2All project. If we move to next page, please. Here we can see the key components that constitute the hydrogen refilling station. This station, as all the others, has been integrated into an existing one, as it normally makes sense, as the existing refilling stations are already located in areas that are strategic for recollecting the traffic, heavy duty and passengers. But if you see on the top right, you see the hydrogen dispenser that looks very similar to a car dispenser, even if the nozzle is different to adapt, of course, for the hydrogen filling. But the use also of the dispenser, it's pretty much the same as you can have in a normal fuel station. Then the container, the Verconnect container, this is in essence the place where we have the hydrogen that is coming from the production plant. Sorry that I forgot to mention on previous slide, but hydrogen is produced green from a production plant in Switzerland, in Niedergosken, where we use water power, hydropower. And the container that you see here is filled at that location with hydrogen, and then is transported to the filling station. You see there are two slots. One is empty and one has the container in it. The operational philosophy is that a container that is full is brought to the refilling station, and it is positioned into the slot that you see empty now, and the one next to it that in the meantime has been used for refilling vehicles is brought back to the production site where it is refilled. And this is a concept that is adopted on all the refilling station. The other elements that are marked here is the middle pressure storage and the compressor and the high pressure storage cooler. In essence, in the container, we have a pressure of 350 bar at the beginning, that then reduce while the container is delivering hydrogen. And this is the primary source to feed cars and trucks as far as the differential pressure allows that. Then we go sourcing from the middle pressure storage that is about 600 bar, and that normally is enough for feeding the trucks container, and for the passenger vehicles that goes up to 700 bar, then we need to use another storage container that is represented at the bottom left. Plus, you see some elements for cooling of the hydrogen. If you go to the next page, here are some numbers of what has been done in Switzerland, and not only on the, and where the H2O program is part of. We have on the road 47 trucks by today, speaking with customers that are ranging from food retailers like Coop we have seen, or Migros, or other logistic company like Galliker, and that are into the transport segment. For the moment, we have run overall with all the trucks that we have on the road in Switzerland almost 2 million kilometers, and delivered 700 of those containers that we have seen into the previous page. So swapped containers from production to a refilling station. So this can be calculated with a net saving of CO2 emission range of 1,500 tons, considering the kilometers that has been run on hydrogen instead of diesel. And the other element that I put here is the longest driven distance in one day is 787 kilometers. This is an element that is very important for the end user, because this means that they can cover a wide range for the delivery of goods and for the logistics segments in which they are operating. The feedback from the truck developer, the truck drivers is very positive on so far, and this is what I wanted to share with this slide. If we go next, I have 2 more slides. So these in this slide, I recollected some of the data that we have collected from the H2O filling station in Rothenburg. And what I believe is most relevant here is to provide some data about how this station is working. We have 24 hours operation of the stations, and on average, what we have seen, the statistics that you see at the bottom left are from February to September, but I have extracted the data from till November yesterday, and there is not significant changes on the averages, on the ranges that are identified here. So we deliver about 16 to 19 kilos on each truck, even if the capacity is higher, but we see there a kind of learning curve for the truck drivers that since in any case the HRS are not so are less, let's say, frequent than normal, tend to fill more often, and that what is necessary. But the refilling time is a very good point, because it says that it's really comparable with the diesel filling station, and then some statistic on the number of vehicles that we see. The other element on the page you can read yourself without me looking into, but again, a good feedback from the operator and good feedback from the users of the trucks. And then we go to the last page, and then I leave a space for questions and answers. So what we are doing in the frame of the H2O program as H2 Energy is continue to accompany and support the operation of the refilling station with all with what is concerned to service and monitoring the performances. We have decided to implement an infrared communication also for the truck nozzle that was not there, and this is something that we are in discussion with Iveco to understand how we can use best this data exchange that can happen during the refilling station between the truck and the dispenser. and then in the next step, there is the tuning on the data that are available and that we want to make available then to the project. So this is an overview of the next steps that are relevant. With this, I am at the end of my presentation. I believe that I borrowed probably a little bit more time than what I was allowed to. And if there is any question on what Andrew or I have presented, please feel free.
Thank you very much, Andrew and Giovanni. Yes, questions. We've noticed, in fact, that there are a lot of retail companies, Carrefour, Coop, Migros, and so on. Is there any particular reason for that?
Yeah, that's a good question. I think it's there's a lot of interest in the technology and in decarbonizing fleets from those kind of logistic companies, and I think that hydrogen is being seen as a possibility to decarbonize that. So a lot of those companies want to be involved in projects such as H2Haul to test the technology and to test how the trucks will work in real life operations. I think in H2Haul we've got quite a nice variety of different sites, end users, operating requirements, mission profiles. And I think across the project, we're going to get quite a good overview of how the trucks will work in those different conditions, but all of those conditions will be real world kind of operating environments. So the aim of the project, we will collect the data, analyze whether there's any kind of particular benefits or differences between the different cases and circumstances, and hopefully get a kind of a nice analysis which can then help further support and give recommendations as to the type of use cases, the type of end users that the technology will be suited for.
Thank you very much. Then we do have a lot of questions about the refueling process. For example, at which pressure the hydrogen is stored on board the truck. You've presented 350 bar, but is there a plan to go towards 700 bar or lower pressure? Then what about the refueling time? You have given to us some data coming from the HRS in Rothenburg in Switzerland, but do you foresee shorter refueling time in other HRS? Can you shed some light about the storage of hydrogen on board and the time to refuel the trucks?
I think perhaps this is one maybe Giovanni can comment on the specific example from the Swiss side. But I think worth mentioning that in H2Haul we are investigating both 350 bar and 700 bar refueling, and we've got those options at the different sites. So again, that's another one where with the analysis we can see how that parameter will make a difference and analyze that as well. And then yes, I think on the refueling time, I think I'll let Giovanni maybe give some already kind of learned experiences from those experiences.
I'm sorry, I have a very bad echo, so I don't understand. I'm not sure I understood fully the questions.
Yes.
But I mean, the refilling, the pressure for the trucks is at 350, and we want to remain on this range of pressure for the truck refilling. This is the concept that we have established. This doesn't require a pre-cooling during the filling of the trucks, and then we believe that this is the best way to approach on this field for the trucks refilling. And then you were asking about the refilling time. I commented briefly. We see times that are really I mean, these 9 to 10 minutes that we see to have a full refill, and we see these comparable to the time for a diesel truck refill, and so it is well in line to serving the customer and satisfying the customer expectations. But I'm not sure that I got to this question the right way.
That was fine. Thank you very much, Giovanni. Now we'll quit the road. We'll go in the air with a presentation on FlySafe, a project coordinated by Safran Power Unit. And with us today, we have the coordinator, Guillaume Albouz, who would introduce to you FlySafe. Guillaume, the floor is yours.
Yes, thank you, Lionel. And thank you for giving me the opportunity to present the FlySafe project. I can't see the slide. Is it? I don't see the slide.
Now you should be able to see the slides.
Yeah. Okay, that's okay. Thank you very much. So FlySafe is the acronym of Fuel Cell Hydrogen System for Aircraft Emergency Operation. This project started in January 2018 and is due to end in September 2022. The overall project budget is more than 7 million euros, corresponding to a FCH-GU contribution more than 5 million euros. And so far, we can estimate the stage of implementation to around 60%. Can you switch the slide, please? The consortium FlySafe includes 6 partners, one from Spain, the INTA, which is a test center that will host our final demonstrator. 2 of the partners are from Germany, the DLR, which is responsible of safety, integration of the final demonstrator, and some testings. And the University of Ulm, also in Germany, responsible of DC-DC converter. And finally, 3 partners are coming from France, the CEA, which is responsible of some part of the fuel cell stacks and the DC-DC converter, the stack DC-DC converter. And finally, Arctic, which helps Safran, the project coordinator, to coordinate the FlySafe project. Next slide, please. So what is the overview of this project? What is the context? The context is that we are in the framework of single-aisle commercial aircraft. So that means mainly Airbus 320 and Boeing 737 families. What is the objective? The objective is to evaluate whether the current emergency power unit system, which is traditionally a ram air turbine. This is a system, a wind turbine, which is deployed under the aircraft in case of total loss of energy of the aircraft. We want to evaluate if the system can be replaced by a fuel cell-based modular system. As of today, there is no other similar product or project known around the world for aeronautical emergency power units. Next slide, please. So regarding the key indicators of the project, one of them is the durability. The target, the project target for the durability is 260 cycles. As of today, on short stack fuel cell stack, we have been able to demonstrate 212 cycles. That means around 75% of the target. So we are on the good track. Next slide, please. The next indicator is the technological readiness level. At the beginning of the project, the TRL level was estimated between 3 and 5. The target at the end of the project is between 5 and 6. As of today, we can estimate that we are around TRL 4. We have still an important TRL increase up to the end of the project, simply because we will have a lot of test campaigns in the next few months that will allow us to claim this TRL level increase up to the end of the project. Next slide, please. So we have technological risk associated to this project, and we have put in place a strategy to mitigate all those risks thanks to 5 important test campaigns on 2 kinds of systems. First kind of system are the subsystem level, meaning the fuel cell stacks. Other kind of tests are at system level. So on short stack test, we have performed start-stop short stack test, durability short stack test, and also hydrogen-oxygen short stack test. All these test campaigns are now over, and all of them allow us to get some confidence on our system, on our design, stack design for aeronautical applications. And they also allow us to confirm the compatibility of our fuel cell stack with pure oxygen at the inlet. Now, regarding system level testing, we will have 2 important test campaigns before the final demonstrator test campaign. The first one will allow us to demonstrate the performance of our anode and cathode loop on a system test rig. The second one will allow us to mitigate every risk linked with control and regulation on the same test rig. This testing should start in DLR around spring 2022. Next slide, please. So, what is the exploitation plan and what are the expected impact of the project? The main exploitation objective for this project is to bring the PEM fuel cell technology to TRL 5-6 for an emergency power unit or EPU application. For Safran Power Unit, the intent is to develop and market an industrial emergency power unit for brand new aircraft. For the DLR, it is to improve the testing framework for fuel cell system for aerospace and automotive application. For the University of Ulm, the expected impacts are, the exploitation plan is to improve the power converter technology. For the CEA, the intent is to improve the fuel cell technology. And for INTA, it is to improve their facility and to become a leader in hydrogen fuel cell system testing. The main impact of the FlySafe project is to mature the technology and paving the way towards applications. This will have impact on fuel cell and hydrogen sectors. This will have impact on environment and also on the aeronautic industry. Next slide, please. We have started the dissemination activities since the beginning of the project, and we have already been able to present at 5 presentations and conferences, and we have already 4 articles in scientific journals. Next slide, please. And to finish, regarding the communication, we try to be there on social medias with a project website, a Twitter account, and a LinkedIn page. This is the last slide of the presentation, so I'd like to thank you for your attention, and I'm ready to answer questions.
Thank you very much, Guillaume. I quite often say that in order for the citizens to adopt the hydrogen solution, they need to witness them, to see trucks, cars on the roads, buses, and so on. But there is one case where I don't want them to witness the hydrogen solution. It's with this Ram air turbine that is there to help as an emergency power unit in case of total loss of energy in an aircraft. So this should hopefully not happen too often. But it shows that there is clearly confidence into the safety of this system so that they can be triggered in case everything else is broken. Can you expand a bit more regarding the safety measure and how you consider safety within your project?
Okay, so first to add to your comment, yes, we have to take into account that many of the emergency power unit system will never be used for their main function during their life, during their project life. So now the safety of the project, the first objective when we have started the architecture work was to make it as simple as possible. The more a system is complex, the less the safety level will be. So at the end, the intent is to try to make it as simple as possible. That means that we should reduce the regulation, the control system to the smallest level possible. So in a few words, once our system is started, there is almost no control and no active regulation on our system. This is really basic control up until the moment the aircraft is successfully landed.
Thank you. I know that weight and volumes are important on board an aircraft. You would like to reduce them to the maximum. How have you tackled to develop the compact fuel cells with a reduced weight?
Okay. So the weight so far is compatible with our expectation. The volume, however, is higher than the project targets, and we still have to work on it, to work on the integration and capacity of this project. Now, how do we tackle the weight? This is by optimizing the system architecture and not to work only on the fuel cell stack, but on the system level to make it as simple as possible and as compact as possible. Then also we are working on brand new concept that can of mechanical parts that can share several functions of the EPU. And so thanks to that function sharing, we can reduce the weight and the volume of our system at the end.
Thank you very much, Guillaume. Now it's time for us to leave the cloud and go into the waves, the sea. We will start with two projects on shipping. The first one will be Ship FC, and the introduction will be given by Mr. Torre Borg from Maritime Cleantech in Norway. And one precision, this ship is not using hydrogen as a fuel, but ammonia into a solid oxide fuel cell. Torre, the floor is yours.
Thank you very much, Lionel, for that kind introduction. And thank you for inviting us to present our project. So the Ship FC project is an answer to a call that was presented in 2019, where the topic was to look at how we could scale up multi-megawatt fuel cells for the shipping industry. And the project answered that call quite directly, and I'll get back into the details in a little minute. But first, some background on the project and where we are today. It's a 6-year project, 72 months duration. So we have now closing up on the end of our 2nd year of production within the project. We have almost 14 million euro budget, whereas 10 millions have been provided by the FCH in a grant. The start was January 2020 with launch on board the vessel, where we had prominent guests and speakers, and we have been attracting quite a lot of attention since day one for this project. So we are very happy to see interest from a broad spectrum of stakeholders. So next slide. Our partners in this project is 14 different partners. We are very proud to have several Norwegian companies. We have Greek companies. We have the University of Strathclyde representing the UK, and the Fraunhofer IMM representing Germany, and PERSE representing France. So it's first-class partners at the very forefront of technology within their respective fields, both in the academia and also for the shipping and the industry sector. The main part of the technology development will take place in the Norwegian group of companies, where we also will perform a pilot. But I think just as important, or even more important, is the work that is also being done by the European partners, where we are looking at further scale up of the system that we are developing and piloting. Next slide, please. So this is a overview of the project, and the primary objective, that is to prove the case for long-range, high-power, zero-emission shipping. So quite a bold statement, and we will prove this by operating a 2-megawatt solid oxide fuel cell for more than 12 months. And it says in the slide that it's close to zero emission. 2 megawatts on the Viking Energy vessel is not enough for them to cover 100% of the operational cases that they have. So by using the 2 megawatts, I think we will reach 80% of their operational time should be within reach when we have these 2 megawatts installed. And it's a very important part for the project that the vessel remain in the operation that it's doing today. As you can see on this slide, they are frequently visiting offshore infrastructure, providing different kind of cargoes. and they have 3 trips a week back to shore where it will be possible to refuel. So the project have been granted 100 square meters on the back deck of a vessel where we can do a retrofit of a solid oxide fuel cell system and an ammonia tank and the other related gas treatment systems. Next slide, please. A secondary objective is to prove the case for the scalable and large-scale zero-emission fuel infrastructure. And we will do this by developing a realistic business model. Of course, without having availability of the fuel, the ship owners will not start adapting their vessels, even though the onboard technology is ready. So this is a very essential part for the project to prove that with this project, not only do we demonstrate the technical solutions on board, we also show that the technology for bunkering a vessel is available and can be scaled, not just for this pilot, but on a global level. And ammonia is already traded globally as a commodity today. So there is quite a lot of infrastructure and ammonia already being traded around the world. So there's possibilities to connect with existing infrastructure. Next slide. So a bit about the progress and where we are today in terms of demonstrating these multi-megawatt fuel cells. You can see from the chart here that it's quite a steep hill to climb. There's no multi-megawatt systems available. So what is now in the lab for testing this year and previous year will have its first test at a larger scale next year, where we do the 100 kilowatt initial test of the system. After that, we will progress and do an onshore test. So we'll do a full scale onshore test of the system before we will install it on board and start the pilot period in year 2024. And the goal for the project is to demonstrate at least 3,000 hours of operation and 2 megawatt of power output connected onto the vessel. This system will run in parallel with the existing LNG machinery on board. So we will basically tap into the electrical system on board and provide a separate power source in addition to what is already installed. And in addition to the fuel cell, we will have a battery pack so that we can perform peak shaving and also manage the need for quick load changes. That's not very compatible with the solid oxide fuel cell technology as it is today. So that's a necessity to be able to meet the industry requirements and also to meet the regulatory requirements for operating close to offshore infrastructure on dynamic positioning. Next slide. Yeah, so for the green ammonia fuel delivery, there's been a fuel commitment agreement signed between project partner Yara, who's a global actor in terms of producing ammonia. So they have signed up and agreed with the ship owner and with the ship charterer, who is Equinor in this case, that they will supply this vessel with ammonia. So we've already signed this agreement, and the details for a specific contract is under development. Of course, this is pending on a lot of development and a lot of regulatory aspects that needs to be further uncovered before we can sign a more detailed agreement. But the intention and the ambition is clear, and the amount needed for the pilot has already been signed out and committed. Yeah, I think we can move to the next slide. As I mentioned, another very important part of this project is to look at the next step beyond this vessel that we are piloting. Of course, it's a limited amount of offshore support vessels out there, and the emissions from this sector alone is not very large if you look at the global shipping fleet. However, if you look at the deep sea vessels that are ocean going and doing ocean crossings, this is where you find the biggest emissions. And to tackle that challenge, this project is also looking into how can we replicate what we learn from this pilot project to larger scale vessels, and then we are talking about up to 20 megawatt of power requirements. So we have shipping companies involved in the project who has delivered vessel-specific data, operational profile. This has been analyzed by the University of Strathclyde, who has merged this data with the learnings we have so far from the fuel cell development and the targeted performance ranges, and they have made a first iteration design of a container ship vessel, 5,000 TEU, with a fuel cell installment running on ammonia instead of the conventional heavy fuel oil. So, of course, this first iteration is built upon a lot of the uncertainty that still resides in the development that we will further detail and uncover and prove throughout this project. So several iterations will be required, but it's very promising to already now see designs for alternative fuels also for the deep sea segment. Next slide, please. A bit about risks and challenges so far. I think the availability of high quality fuel cell stacks is of course essential for a project like this. And our project partner, Prototech, has therefore entered into a frame agreement with a known stack supplier that they have been working with for several years. So I think that's a good mitigating measure. And a more generic challenge that we see, and I'm sure here can relate to this, that it is at the moment increased lead times for deliveries, maybe specifically for electronics. I think it's challenging to get power electronics these days. So we're trying to forward the RFQ process as much as possible, but of course it needs to be in line with what we see in terms of results from the lab. So we cannot push things too much forward. So these are some of the challenges that we have seen so far and that we are working to mitigate as best we can. Next slide, please. In terms of exploitation and the expected impact, we have targeted a lot of public stakeholders for this project. When we're working, we see a lot of interest, as I mentioned, from the public sector, maybe especially in Norway, since we are seated in Norway. We do get attention from all the way up to ministerial level, where they are interested in this project, and they want to use it as an example when they are trying to adapt the policies as we move forward. So that's a very important part of what we are doing, is to reach out and get in touch with these public stakeholders. And so far we see great interest even long before the pilot is ready. Further, the ship operators, of course, are very interested in what's ongoing, and we receive continuous requests for taking part in the project and also wanting to learn more about it. So I think that's it shows that the solid oxide fuel cell technology and also the ammonia fuel is something that is considered highly relevant for the shipping industry. And further, we see suppliers that are kind of searching for their next, the next direction to take place within the green shift and adapt their business models. They are curious to see how they can this project can help them sort of pave the way for what the future may look like for suppliers. And the data that we use is, of course, research data, as shown here, with the different designs. And when the demonstration is ready, of course, that's a very good source of exploitation for us as we move forward. Next slide, please. Yeah, and some of the communication and dissemination activities we have performed so far. We have launched a website. We have a LinkedIn page. We see quite a good traction on both of these. We have been in several conferences and papers have been written. So also when we are arranging webinar in the ShipFC regime, we have good attendance, and we see a lot of good dialogues coming out of these meetings. And I think it's safe to say that it has a global reach. We've been in magazines in Japan and Russia and basically more or less all over the world. So very exciting project, and I'm looking forward to be able to share more results in the coming years when we when the scale up and the testing is taking place. So thank you very much for your attention.
Thank you, Torre. Indeed, quite a lot of attention into ShipFC. For example, the owner-operator of the ship, Eidesvik, signed an agreement, I think it was 3 weeks ago, that it will develop 2 additional vessels based on the result from ShipFC. So that's clearly already a success, even without having put the fuel cells and the ammonia on board. One question regarding the ammonia. You has indicated that the bunkering, how does it work? Will it be through swappable containers? Can you explain a bit more how this ammonia will be stored on board the vessel?
Yes, indeed. It's we actually last week we went to the harbor that this vessel is visiting 3 times a week, and that's quite a busy harbor that's focusing on the logistics for the Norwegian offshore sector. So on the quayside there, you have lorries, trucks, cranes, and you have also, luckily, you have actually shore power connections. So quite a few of the ships are connected to these shore power infrastructure as well. But we discussed with this offshore base, how can we make sure that we can bunker ammonia in a safe way, because it is a challenging substance to manage. Of course, it's toxic, but at the same time, we see that the knowledge we have within the project with our partner Yara, they have plants all over the world, and we have luckily gotten one of the senior personnel who's been a responsible HSEQ manager for a lot of these plants is involved in the project. So the next step now is really to get into the details and see how we can do this without disturbing the ongoing work at this site. And also, how can we do it without disturbing the turnaround time for the vessel? So I think for the technical part to get the ammonia on board, that's something that's solvable. But if you look to all the other aspects that we need to take care of and all the other stakeholders that's connected to this vessel, that's where it becomes challenging. But of course, it's only one way to do it, and that's through a dialogue and starting with concept considerations. We will move on to selection and then find our path to engineer a safe system. And finally, I think it's also worth mentioning how focused Yara is also on the human specter in all of this. I think also training and making sure that personnel operating this technology needs to be aware of how it's done, and I think the safety part and the human part of that shall not be underestimated as well.
Thank you very much. You said that the ship will use green ammonia. Still, there could be some emission or formation of, especially of NOx. Is it something you look at within the project? And if yes, what are the early results about this?
Yes, this is something that we are looking at, and it's a close collaboration between Pototech, who's developing the fuel cells, and Fraunhofer IMM in Germany, who's looking at how we can create an exhaust treatment system that manage the formation of NOx and N2O. And so far, the results have been very good in terms of eliminating any of these gases in the exhaust.
Thank you very much, Torre. Now we move to the next speaker, Mr. Christian Frédéric Berton from the project H2 Ships. So H2 Ship is not a project supported by the FCH, but by another program called Interreg, and it will show synergies between inland navigation or maritime shipping projects among the large family of funding program, Interreg, CEF, or even the FCH. Christian Frédéric, the floor is yours. Thank you.
Thank you, Lionel. I'm very happy, as you just mentioned, that we are able to build this bridge between different programs. As you said it, and it's going to be recalled in the next slide, when the slides come. H2 Ships is funded by Interreg Northwest Europe. It's a project which started in 2019. It had a kind of a difficult start, and it will last until 2023. We are, well, this summer we were at about 50% implementation of that project, which has a total budget of about 6 million euros. Interestingly, and that might be a little bit different due to the different nature of the funding program compared to the projects which have been presented before, the partnership, I think, does mix maybe a little bit more different types of partners, because we have private companies, we have 2 universities, Birmingham and Delft. We have port authorities, which is an essential part of our projects, and we also have NGOs who are interested in this topic. While we go to the next slide, please, I would like to give a few words of, to say a few words about the context, because this is the second presentation about shipping. First of all, shipping is in a wide world which covers quite different realities, and you could make 3 big categories between inland shipping, short sea shipping, and deep sea shipping, and in each case, the situation is quite different. Similarly, with other types of transportation, the shipping sector as a whole is facing this double challenge of reducing the greenhouse gas emissions, but also reducing local air pollution. And that was just mentioned before with the question of the NOx. And as the other sectors is desperately looking for alternatives, what makes it a little bit different compared to, for instance, road transport is, I think that the shipping sector has some specificities. I would like to highlight 3 of them. And the 2 of them are mainly challenges, while the third one may be an opportunity. The first one is that even within each of these 3 categories that I described, if we, for instance, look only at inland shipping, the fleet is made up of an extremely wide range of ships, and for each ship you have a wide range of operational constraints, which means that the needs and the possibilities in terms of energy transition in shipping are highly dependent on each application. So there is absolutely no one-size-fits-all solution. And it has to be all tailor-made, almost, I would say. That makes it a little bit more difficult. What makes it also particularly difficult is the very long investment time you have in ships. When you buy a truck, I think you have a duration in mind of about 10 years. But when you are talking about ships, it's 30, 40 years, which means if we want to have carbon neutral, zero emission shipping sector in Europe by 2050, we need to start building these new ships right now, or at least make sure that we build them in a way which will allow them to be retrofitted in the next years. The third specificity is that ports have this essential role in the shipping sector, and that coincides with, I think, what is the French view on the development of the hydrogen infrastructure, where a lot of hope, a lot of emphasis is put on the role of ports, because with a specific position in the industry, in the transport network, in the energy network, the ports are the interface between all these aspects, and they are of course facing, as other aspects of the industry, the challenge of the decarbonization, but they also have sometimes very interesting strength. Some of the ports in Europe are closely connected to offshore wind parks. They are connected to inland waterways, which are a very ecological way of moving things around Europe. So this is, I think, an idea. It's an idea which is not on this slide, but I wanted to bring forward because it was behind the construction of this project. Now, the H2Ships project, it has a quite broad objective, which is to help hydrogen to become a solution for the transition of shipping in Northwest Europe. That's the belief of all the partners which have joined this project. Another belief, as I just explained before, is also that this will happen if the ports can play an important role in the creation of local green hydrogen ecosystems. To do this, we need to address challenges in 3 different fields. The first one is the context, especially the regulation context, but not only. The current situation, the way we work, the way the industry is built, creates some difficulties when we want to develop these hydrogen ecosystems. So in this project, we are working on the identification, for instance, of showstoppers in the regulation, what can be done, where are the big problems, what is preventing motivated industry partners to create these ecosystems. The second field is the question of the market. We can remove all regulation problems or create the right regulatory framework, but if we don't have the right companies talking together, if we don't have the right ways to do the investment in these new types of ecosystems, it won't work. So that's another aspect we're working on. And the third one, of course, is the technology. And that's the topic of the next slide, which is showing what we are doing in one of our pilot projects. So if we can go to the next slide. Yes, thank you. In the Port of Amsterdam, we are developing a new passenger vessel. So this is not a big one. It's not the Viking Energy. It's a small vessel which will be able to sail around in the canals of Amsterdam. It is the representation vessel of the Port of Amsterdam, which means it has a high symbolic role, because when some members of the royal family in the Netherlands are coming to visit the port, they will use this ship. This will be with an electric motor and a fuel cell. This is actually not something really new in the world of shipping. The new thing about this ship is the way the hydrogen will be stored. Instead of traditional high-pressure vessels, the hydrogen will be stored in the form of metal hydrides, more precisely sodium borohydride. This is not that easy. There is a benefit from this compared to refueling with pressurized gas, which is that you are working with the powder, or alternatively it can be also in a liquid form, at ambient pressure and temperature. So this is expected to be in many situations, a very important benefits in terms of refueling. We are in close discussion with another Interreg project called ISHI, where there's a range of ships which were supposed to be built or transformed to hydrogen. And in one of these cases, there was a showstopper after 1 year project, and that was because of the impossibility to do the bunkering, if I'm correct. So that can be a very important aspect. Of course, to get these benefits, there's some price to pay compared to the standard solution, which is already currently available, which is 350 bar pressurized hydrogen. And the difficulty is that you are not having only one pressurized vessel in the ship. If you want to use metal hydrides, you need to have a tank to store the fuel. Then you need to have a reactor when you will mix this fuel with water and release the hydrogen. Then you need to have a tank for the water, which you need for this reactor, and you need to have a fourth tank to put the spent fuel in, because you have something which remains after you have extracted the hydrogen from the sodium borohydride. So alone, the integration of the whole system in the ship was a challenge, and we can happily say that this challenge has been successfully met. That's what you see on the picture. You have the schematic integration of the whole system, including also the batteries, the fuel cells, and the electric motor in the ship. So the design is ready, and the ship is going to be built starting next year. The Port of Amsterdam is currently about to launch the public procurement procedures for that ship. Can we go to the next slide, please? I talked about the role of ports and said we have 3 ports in the project. The Port of Amsterdam I've just been talking about, and I'd just like to talk about the Port of Paris. In our initial vision, we wanted in each of these 3 ports to address one of the 3 main bricks of this ecosystem. In Amsterdam, it would be the utilization of the hydrogen on a vessel. In Ostend, the emphasis is more on the logistics, on how you bunker the hydrogen. And in Paris, we also wanted to investigate the local production of green hydrogen. We have defined a series of studies for the case of Paris, which try to identify, let's say, kind of pave the way for the first green hydrogen ecosystem for shipping to be built in Paris. We have highly motivated partners around that idea. To be absolutely clear, at the very beginning of the project, we also hope that we would be able to implement such a solution in Paris. We have learned that it's not that easy to start, well, even with a lot of motivation, to start such a thing. So we have taken a step back and defined a series of studies which allow us to see what can be done, what should be done. So that goes from a market study to a case study with one of our partners who is really looking at building a small fleet of hydrogen push boats for their needs. And in between, there are different steps and questions, such as, are there any locations close to the Seine River in or around Paris where we could imagine that someday we will build a small electrolyzer and distribution station for the ships? What are the actual needs of the ship owners operating in and around Paris? How can we bring that innovative fuel to their ships? All these questions. So each one of these questions is the subject of one of the reports we are preparing, and luckily we have most of the stakeholders, especially the ship owners, around us. We have regular meetings with them, and that's how we can progress on this ecosystem approach. Can we go to the next slide, please? As part of the Interreg program, the H2Ships project has a lot of emphasis on cooperation between the countries, and one of the aspects to bring this cooperation forward is, of course, communication. So in the initial plan, seminars, conferences, dissemination events were supposed to be a very important part of the project, and as you can imagine, this has been quite reduced with the pandemic. We've had the feeling that the webinars are good. these seminars would bring the most of their benefit if we can have them live. So luckily, as you can see on the picture, we were recently able to do something live in Paris, a seminar to present the progress of H2 ships, but also other projects, because there are lots of other projects in the same area in Europe. We have also produced a couple of videos. Some more will be coming, especially when the ship in Amsterdam will be sailing. And we have a quite intensive activity on LinkedIn and Twitter. Next slide, please. Just to finish, I would like to highlight one risk and one challenge we have identified in this project and we've learned about. The first one, I just said it on the slide before, there are many projects, many very exciting projects which have been started in the past, which are just about to be started, which address the question of how do we decarbonize the shipping sector. Some are focusing on inland shipping, some are focusing on fuel cell solutions. So for us, it remains a challenge to keep an eye on all these projects, make sure we get the right connections, and make sure that we don't do things in parallel and lose time, but that we have complementary approaches. So luckily, after 2 years on this, I can see that the people doing that job when they select the projects are doing it in the right way, and probably also talking to each other beyond the individual funding programs, because I didn't see any big overlap until now, but still this is a challenge to make sure that we invest the energy of all the stakeholders in Europe in the best way to reach our goal, which is to propose a pathway for the transition of shipping. The second part of the slide, well, it's both a positive signal and also a warning. I don't know if you've heard about the ship which is pictured there. It's just an example. It's not the only one in this case. But this is a fuel cell ship which has existed. It's the Nemo H2, which has been built for Amsterdam. This one has never been sailing on hydrogen as far as I know. The reason was it never got the authorization of the city of Amsterdam to do the bunkering operation. So that's one big risk. I have the feeling, given the fact that we do have a couple of hydrogen ships already sailing in different countries in Europe, that this regulation or authorization problem is at least partly solved. I know that there's a great willingness of the authorities such as CCNR or the ministries in different countries to provide solutions. So I'm hopeful, I'm confident that this problem will be solved quickly. There's another one which is not depicted here, which is the Alsterwasser, which sailed in Hamburg. And this, I think this stopped the operations for other reasons, which are just the lack of a real business model. And I think that's where the biggest risk is still there today. We have seen this already, and even within the H2 ships project and the ISHI project I mentioned just before, that in some cases, even with the best technologies available, the best will, the best technological use case, sometimes there is a big showstopper, which is the business model. So I think that remains the challenge, and I hope there will be some solutions in the future too. That was the end of my presentation. I think there's just a couple of minutes left for any questions. Thank you.
Thank you, Christian Frédéric. On your last slide, I would like to reassure you that indeed there is a wealth of project looking at hydrogen ships, be it for inland or short sea shipping. But all these project coordinators know each other. And in fact, we already have had some combined seminar. And so there is a very neat transfer of knowledge, either between the Electra project, which is supported by NOW in Germany, with Flagship at the FCH, with your project H2 ships from Interreg. So indeed, there is a good cohort of projects that are looking at similar yet different aspects in each case, but exchanges are there to speed up the introduction of hydrogen as a marine fuel. There is one question which relates to the sodium borohydride, and the question is the following: how do you recycle the byproduct of the sodium borohydride reaction, and with what yield? Is it something you would know, or?
That's a very good question, and I like it because it allows me, well, to say to show both sides of things. One is, of course, you've put the finger on the right problem. Of course, for the whole borohydride solution to be viable, it must also have in total a correct yield. On the other hand, this bringing forward one major problem with this technology also allows me to bring forward one positive result of the project so far, which is that given the positive progress of the design studies on the ship in Amsterdam, several stakeholders interested in this technology, specifically in the Netherlands, they have said, okay, now we believe that it will work to integrate this in a ship. Now we have to look at the regeneration part of the spent fuel. So they have created a consortium, I think it's about 1 year ago now, called Solid Hydro Regen, which is specifically looking at this question. So I know honestly, I think it is still an open question. There are ideas, there are technologies being developed. I use the plural because I know from our partner TU Delft that there are 2 ways to recycle the spent borohydride. It is still at a rather low TRL, but again, given the positive outcome of the design study so far, there's a strong willingness to progress on the fuel regeneration part. So I hope that that there will be some results on that in the next years too.
Thank you very much. We are reaching the end of our session, so I would like to congratulate you once again to Andrew, Giovanni, Torre, Guillaume, and yourself, Christian Frédéric. We have a 10-minute break, and then we'll continue with the session about the building blocks for heavy-duty transportation at 2:30 Central European Time. Thank you very much.
Good afternoon, ladies and gentlemen, and welcome back to the Program Review Days 2021 for another parallel session. This session will be dedicated again to transport. My name is Pietro Caloprisco and I will be moderating this session. Early this morning, my colleague Lionel brought us for a very interesting multimodal journey where we have seen our demonstration projects, what we are doing on the roads, in the skies and in the sea. Now it's time to step away from there and we are going to look at what we are doing in our laboratories and factories to make all of that possible. Because behind the deployment of these fleets, there is a lot of work at the research level. Today, with the building blocks, we will be looking into that. So how we are working to improve all the components that are at the base of the fuel cells mobility solutions. We will be looking at manufacturing and quality control projects, at tanks and compression solution for hydrogen refueling station. Of course, these are just a selection of the many projects that are ongoing in this domain. So without any further ado, I would like now to give the floor to the first speaker, David Colomar. He is the CEO of Efitec and he's also the project coordinator for the COSMIC projects. The COSMIC and COSMIC XL in particular are the subject of the presentation today. So David, the floor is yours and we are looking forward to hear about your achievements and future projects.
Hello, everyone. Thank you very much for Pietro for the nice introduction. I'm very glad to give you today an introduction of two very important projects that I am coordinating, which are the COSMIC and COSMIC XL project. My name is David Colomar and I'm the coordinator of these two projects. Next slide, please. Oh, sorry, no, COSMIC, it's fine. So in the frame of the COSMIC project, so COSMIC is a project that started in 2017 and that address innovative compression technologies for small-scale applications for hydrogen, and this is about refueling and also storage. The project is now finalized, and so I will be very happy to give you a few highlights about what we've achieved during the project. Next slide. We also have a second project, which is COSMIC XL, which is still ongoing. It started 2019, and we are still working on innovative compression technologies. But here the aim is to further improve the technology and especially to scale it up for different applications in heavy mobility context. I want also to highlight the consortium of these two projects, which is the same. It gathers 5 companies: IFER, Mytec, Nel Hydrogen, LBST, and Steinbeiß from 3 different countries, Denmark, Germany, and France. Next slide. So in the frame of COSMIC, the idea is to combine 2 different compression technologies in order to achieve an optimized solution for addressing the issue of hydrogen compression. Basically, the idea is that we will have first a compression based on an innovative technology that is so-called metal hydride technology, which we will then combine with a mechanical booster to perform the last step of the hydrogen compression. The concept of metal hydride technology consists of absorbing hydrogen within so-called metallic alloys, which have the possibility to build hydrides with the hydrogen. When we heat up these hydrides, we have the possibility to desorb the hydrogen, so to release the hydrogen at a much higher pressure. So if we perform cycles of this absorption, desorption concepts, we manage to create a compression effect. And that's what we do in the frame of COSMIC. What is very interesting is that this technology based on metal hydride is not a mechanical one, so there is no more moving parts. So we replace basically a mechanical effect with a thermochemical effect, and therefore we solve a lot of issues related to mechanical technologies, including noise pollution, including wear and tear, including a lot of electricity consumption, including leakage issues, and so on and so forth. In the frame of the COSMIC project, we had different objectives, including getting rid of critical raw materials, reducing investment costs. We wanted also to reduce the energy consumption compared to the state of the art, and we wanted to improve maintenance costs and lifetime. Next slide, please. In the frame of the COSMIC XL project, which is the follow-up project of COSMIC, we want to use the same concept, but now we want to address especially the topic of heavy mobility. As you may have heard this morning, there is a very clear trend towards the use of hydrogen for heavy mobility applications. These include trucks, buses, trains, ships, airplanes, and they all have very specific and different constraints which have to be fulfilled. And therefore, in order to address these emerging use cases for hydrogen, we need to have solutions, including compression solutions, that are very modular and that are well fitted for all this broad range of use cases. And that's why we want to achieve, that's what we want to achieve in COSMIC XL. We still have similar targets as in COSMIC, but we want to go one step further, especially in terms of OPEX reductions and in terms of scale up. Next slide, please. So here, I now would like to highlight a few results of the project so far. First of all, I'm very proud to say that in the frame of the COSMIC project, we have achieved pretty much all the KPIs that were defined in the project. I don't want to explain all of them because I would need much more time, but just would like to give you one example in terms of pressure. We have managed to have in a scaled up prototype a compression effect from 25 bar up to 429 bar, which is a first-class result, and which is very interesting because it means that with the metal hydride compression technology alone, we already managed today to fulfill the requirements of a wide range of applications, including forklifts, buses, trains, filling centers, so all the applications that need pressure levels below 430 bar. Next slide, please. I also would like to introduce you the TRL5 prototype that we've made and tested in the frame of COSMIC. So this prototype was first designed by the members of the consortium. We defined the different components, the different subsystems, the integration of all of them with their specific BOPs. We've made safety analysis. Then we built this compressor all together. We assembled the different subsystems and we tested it in our facility at Fraunhofer ICT in Karlsruhe, close to the IFER Institute. And this TRL5 prototype has been operated for a couple of months. And this is, to the best of my knowledge, the largest existing innovative compressor for hydrogen worldwide. So I believe we can say today that thanks to these achievements, Europe has become the world leader in innovative hydrogen compression technologies. Next slide, please. One other big achievement I'd like to highlight what we've done in the project so far is the development of innovative materials for this compression technology. So we have identified a wide range of possible metal hydrides that would be adapted to the project. We have made them, we have developed ingots of metal alloys, we have crushed them, we have tested them, we have performed a lot of iterative tests to achieve compositions of hydrides. Here I want to highlight a point. There were already existing metal hydrides, but some of them were including rare earths and other critical raw materials, and we managed to get completely rid of them. And also we managed to have materials that are not only existing, but also well adapted, well fitted to the requirements of compression in terms of capacity, in terms of lifetime, in terms of pressure, temperature ratios. And this is also, I believe, a very big achievement of this project. And all these materials can be sourced in Europe. And that is also something very important, I believe, for the sustainability and the future of the future industrialization of the project. Next slide, please. Beside the very technical achievements, I just would like to mention that there were also non-technical parts of the project. We have done a web page, we made a video of the project, and we had a final event gathering about 100 people from the industry. And these transversal activities, let's say, are, I believe, quite important because they help to let's say, communicate better about the technology. We still need to explain to the population, to the politicians, to the rest of the world, let's say, why these technologies are important and what can be done with these technologies. And that was also one important part of the COSMIC and COSMIC XL project. Next slide, please. Finally, I just would like to conclude with a few remarks. The main findings are the technology works. That was demonstrated already in COSMIC. But nevertheless, there is still a lot of work to do in order to bring it to the markets. So especially in terms of purity management, there's hydrides, they still do not really like working with non-pure hydrogen. And there we have still work to do to improve that. There is a lot of things to do on the thermal integration to further reduce costs, and that there are things that have to be, so work has to be carried on these activities. We also identified a few challenges. I don't want to highlight the COVID issues because I think that's pretty clear for everyone that this was a big challenge to deal with. But I also would like to say, to highlight a non-expected challenge, which was actually the difficulty to find basic hydrogen components. We actually thought when we started the project that it would be more difficult to make the innovative part and that the rest would work, but actually that was pretty much the contrary. With the innovative component of the project, we had not that much difficulties, but instead we had a lot of troubles finding the appropriate valves, fittings, sensors, and so on and so forth. And I think there is here a clear message. There is an urgent need to strengthen the European supply chain on H2 components, including the very basic ones. And that is something I believe we all have to work on collectively. And then just as a next step, we will start now the construction of our second prototype, the COSMIC XL prototype, which will be again a scaled up and a more performant prototype. And we will also start the demonstration of the technology within a real hydrogen refueling station. And this will be done in a third project, the project COSMIC Demo, which has started at the beginning of this year. Thank you very much for your attention, and I'm very happy to answer your questions if you have some.
Thank you very much, David. That was a very interesting and refreshing presentation. It's also very interesting to hear about the EU leadership now in this specific segment of the innovative compression for HRS. I just had one question about the next step, the future. So you already mentioned that some work needs to be done to further optimize this compression solution, and also that now we are working on the COSMIC Demo with the deployment of the second prototype that will be tested in real life. What is the timing now for bringing really this thing to the market? Because we have heard this morning again about the heavy duty application, and you mentioned it yourself. There are a lot of expectations by 2025, 2030, already the trucks, they have a stringent CO2 emission targets. This is a good opportunity for the zero emission vehicles. But this large number of trucks will also need the appropriate infrastructure. So it's a great opportunity for also a company such as the one that has been created on the back of the COSMIC projects to commercialize this technology. But what is the timeline? How long is it going to take to get there? What is your outlook here?
As you know very well, Pietro, the COSMIC Demo project, which has started in 2021, will last until 2023. And I believe 2023 is a very good timeline for commercialization. So I'm optimistic that by that date, by the end of the COSMIC Demo project, we will have a product which is pretty much a market product. So we'll be able to start commercialization around that date. I would like to mention that in parallel to the demonstration project, we already have like pre-commercial projects, which means that we perform this demonstration. We have, of course, COSMIC Demo. We have a couple of clients or prospects that are already contacting us to sell them products or to provide them technologies in the frame of co-development contracts. We signed already some corporate deals with prospects. So the commercialization is going to start very soon. And I'm confident that by 2023, we will have products that will be pretty much at the same level as what there is today with standard technologies.
That's great to hear, because indeed these are quite urgently needed these solutions. But still commenting on the fact that you said that you were a bit surprised on the lack of availability of components that you would have thought they would be off the shelf readily available. Now, I'm well aware that you do not have a crystal ball, but do you think that this could become a bottleneck for you in your projects in the next coming years, if you want to upscale and start to sell this solution in mass?
Yeah, it is, in fact, an issue. Today, we are struggling very hard to find European-made components in some of the markets. We do find components. There are always solutions. We manage to build the machines, but sometimes we have to rely on non-European solutions. And even if they look quite basic, they can still be, they can represent an issue in terms of independence and in terms of value chain for the European economy. So each time we buy a component, we ask our suppliers, where does the component come from? Where do you produce it? And it's happening very often that even European companies tell us, yes, we have products, but when we dig a little bit more, we realize that it's made in Asia or in North America. And there, I believe we've seen over the last 2 years how important it has become to be independent on overall supply chains. By the way, not only for hydrogen. And I think it's getting more and more critical to make sure that we can do everything by ourselves. Otherwise, there could be one day where I cannot be able to build my machine here just because I cannot get the valves or I cannot get the components that I need to make it. And that could be a risk because that could lead some other manufacturers to delocalize their production somewhere else than in Europe. And that, of course, would be a shame. So it's something that we all have to do together. We have to support ourselves. I believe the component manufacturer or the technology manufacturers like us need to favorize the European components as much as possible. I also believe that the end users should favorize the use of systems produced in Europe, and all of these together will contribute to strengthen the European value chain.
Thank you, David. Excellent. I think that that was a very clear message and it is being heard. So thank you very much. That concludes the first presentation dedicated to the hydrogen refueling station. Now we move on from the hydrogen refueling station. We go on with the tanks. And we are really glad to have here also with us today Axel Seifert, who is the Business Development Director, High Pressure Vessels at Plastic Omnium. And Axel, we are looking forward to hear more about the project TAHIA, so Tank Hydrogen Automotive. Please, the floor is yours.
Thank you, Pietro. Yeah, first of all, I would like to thank the European Commission, FCH-JU, for inviting me, and also having funded a lot of the development projects, not only TAHIA, but also the project which preceded this project. I've been, for your information, my personal background, for nearly 30 years, I was independent entrepreneur developing technologies using composite materials. I've started in hydrogen storage business in 2004 with a project called StoreHy, which was probably one of the first industry project financed by the European Commission to look at the technological barriers of hydrogen storage and with a will to catch up with the technologies which were already available in North America and Asia. So, and I think this TAHIA project is a real milestone for us, or for me in my career. I'm very happy to present the work we've done for the past 4 years. Just for your information, so I was having my own companies for 30 years. And then in 2017, my companies and the technology we developed was acquired by Plastic Omnium, a large automotive tier 1 supplier focusing on energy storage for passenger vehicles. I think this also demonstrates how the development we made was appreciated by the industry. Anyway, coming back to Taya, the call year was 2017, and it's not about heavy duty application. It's the focus was at the time on passenger vehicles. So the call was about improvement of compressed storage system in the perspective of high volume automotive applications. So clearly focusing on mass market, clearly focusing on passenger vehicles. Project dates was from 2018 to 2020. It has been extended until this year, mainly due to obviously the COVID crisis and also some project adjustments, which led to this extension of the project. Today, I think we are completed, except for reporting. We did all the technical tasks and are just finalizing the reports. The project was funded with close to 4 million euros, which all came from the FCSJU. Next slide, please. As to the partners, the consortium is led by the industry. So Plastic Omnium is the project coordinator, with from France, Regi and Apsiski, some, I would say, historic partners with whom we've been working on previous projects to develop, in the case of Regi, develop liner technologies, and Apsiski is a company focusing on project management. And then we have a large participation from German companies, Polarex Partners, specialists in costing and price analysis of components specifically for the automotive industry. Theo Chemnitz, they helped with new ideas about filament winding or winding process to manufacture the tanks, to improve the productivity, and also they contributed on the simulation of during the filling and defueling of the tanks. Arnleg is a renowned specialist of on-tank valve system and gas handling units, obviously very important in this project. BAM, Bundesanstalt für Materialforschung und Prüfung in Berlin, a renowned partner regarding the safety aspects of a tank. And then last but not least, Volkswagen, German OEM, who at the time had some projects or some vision about the use of hydrogen fuel cell cars for automotive application. Next slide, please. So to summarize the project, I think when we look at the objectives, we can see where the focus is. Well, first of all, to do the preparatory work to provide a compatible hydrogen storage system with high performance and improved safety features, which is health, safety, environmentally responsible. The TRL level to be obtained was 6, so it's really something which is close to be introduced to the market. Second objective, provide a compatible H2 system fit for mass production and being cost competitive according to the specifications of the OEM. So it's really not about developing a hydrogen tank, but developing a hydrogen tank which really meets the automotive requirements on a real test case. And then third objective is obviously to actively contribute to the codes and regulations, standards to try to bring our experience about safety and functionality, durability of the tanks to be included in the worldwide standards. Next slide, please. In short, briefly, based on the specification by Volkswagen, hydrogen tank system was defined with a single tank, which would be mounted in the longitudinal direction of the vehicle, mounted under the floor. It includes the on-tank valve, gas handling tubing, filling receptacle, and also obviously the frame of the tank fasteners. The capacity of the tank should be 5.3 kilograms of hydrogen at 700 bar with a gravimetric efficiency of 6.5%. So gravimetric efficiency, which is also one of the KPIs which is monitored by the let's say annual work plan evolution of Hydrogen Europe. So gravimetric efficiency is defined as being the mass of hydrogen divided by the weight of the tank. Okay, so 6.5. I will come to this later, what we achieved. And then focusing on an annual production volume of 20,000 systems per year, and targeting a cost per kilogram of hydrogen stored of less than 500 euro. So this was basically what was defined by Volkswagen at the start of the project to define which way the activity should go. Next slide, please. So if we look at the results, I mentioned the gravimetric efficiency, and you can see that we obtained this gravimetric efficiency of 6.5%, where at the beginning of the project it was 5.3%. These values come, as I said, we have a long history of participating at those projects, and one of the projects with the comparative technology was the Copernic project, which from 2013 to 2016, where we reached a tank with a gravimetric efficiency of 5.3%. Now, another project, the HyPhone project, we increased the gravimetric efficiency, and with the Taya project, obviously we were able to further increase this. But I would say the main work to achieve this goal was obviously to optimize the design. But what we saw also on the market, the evolution of the carbon fiber specifically developed for this application, really helped to reduce the weight of the tank. So this was one KPI, and obviously the next slide, please. Another KPI are the cost of the hydrogen storage, and there we can see in the red line again the evolution we made for Taya, the cost calculation based on the technological choices we made, and we can see that we actually over-delivered on this target, where the specification was to find a storage system with a cost of a maximum 500 euro. We are there at 450 euro per kilogram of hydrogen. So this was quite a positive evolution. Now, if we look at the next slide, please, showing the risk, challenges, and lessons learned. Well, first of all, to our disappointment, we know that today in Europe, for the passenger vehicle, except for BMW, all OEMs are really looking at battery electric vehicles. So unfortunately, the market we had hoped for in the beginning of the project in Europe is not there, at least for the next 3 to 5 years. We will see what will happen after that, but that's the case. But on the other hand, the good thing is also because the tank we developed is quite large, there are opportunities, and we see and we have had several presentations already on transportation, heavy duty vehicles, but there's also a focus on light commercial vehicles, which is very strong for the last mile delivery, and those tank systems are actually very close to what we've seen in the passenger vehicles, and a similar architecture can be used. And if we look at the success we have, really over the years, we were really able to develop tank technology which really sets a new worldwide benchmark. Next slide, please. Now, if we look at the results, next slide, please. Thank you. One result of TIA is what you will find in the new TRIA of Hydrogen Europe, which is a strategic research and innovation agenda for the next years. You can really see that the cost calculation of the storage tank has been adopted by Hydrogen Europe as a guideline to where the industry needs to go. Just one comment on the cost of the hydrogen system. You can see everything which is dark brown colors to the right. This is related to the cost of the raw material. And the raw material is mainly, this is the dark brown piece of pie, is the carbon fiber. And the carbon fiber, this is really something where we see a challenge for the future, because the requirements, the need of carbon fiber for the automotive vehicles to store hydrogen really surpasses any application known today in composites processing. So it's much more carbon fiber than we can have, and this thanks to BAM in Berlin, Georg Meyer and his colleagues, to actively contribute to the new regulation. So there's a new draft which has been finalized last month, which will be submitted to the different regions worldwide, to the contracting parties who will adopt then the new standard, the new regulations by the end of 2022. And I think BAM really did a very good job in contributing with some of the results we generated in TIA. And last but not least, and this will be my final slide, I'm personally very happy to be able to announce that we were able to secure a very large order from Hyundai, one of the leading hydrogen vehicle manufacturers in the world, to supply, as of 2023, production of 40,000 tanks per year. And obviously there are a lot of results which were very useful to be able to sell this technology to Hyundai, and those are exactly the key issues we looked at in the TIA project, which are related to cost assessment and streamlining. So we were very, very competitive in our offering, mainly also because we have an optimized tank design. So the design which we used for the TIA project, we could use the design and scale it to the size of the tanks required by Hyundai. And obviously also we are developing a new production line which improved productivity, and this also thanks to the work which has been done in TIA and the previous projects. And this brings me to the end of my presentation, and I would like to thank you again.
Thank you very much, Axel, for this very interesting presentation, and congratulations also for the commercial success with this very large order. Though I would share with you, it's a bit rather disappointing to see that here at home in Europe, you were not able to secure such a large order for the product that you have developed. At this regard, you partially touched upon this, but I was wondering how much of what you have developed in TIA would be adaptable and transferable to heavy-duty applications. Of course, there the requirements are a bit different in terms of pressure and the volume of hydrogen that needs to be stored on board. But you have been there around since 2004. You have a great experience. How difficult it would be for you to start to tackle that transport segment?
No, I would say obviously it's just easier to start with a small tank rather than focusing on a big tank, but the technology is the same, and the hydrogen storage tank is a very simple component. We just have a liner, thermoplastic liner with some metal end pieces, and then the carbon fiber reinforcement, and that's all. So we can definitely, everything related to design and processing, we just need to scale it up. And as we speak, we are obviously working on development of larger tanks. And by the way, we already have a project to supply tanks for 350 bar for a bus project in Germany. And we have actually in Belgium, in one of the production plants of Plastic Omnium, installed the first pilot line to produce 10,000 tanks per year. And actually those tanks, interesting enough, they are not only used for the buses, but we are also using those tanks in projects like H2All projects. You've maybe heard from the train project in France with Alstom. They are all, it's all the same tank, with the same tank which is used in different applications. So it's really very versatile.
Okay, perfect. That's good to hear. And in terms of looking ahead, in terms of further development of the product, where would you see like the biggest challenge? You mentioned carbon fiber, the use of raw materials. Is this the main thing, or is there also the manufacturing technique, the new geometry?
Yeah, it's well, first of all, it's for me the acceptance of hydrogen fuel cell technology for passenger vehicles, because I still see a major market there, but there are some roadblocks which are not related to technology, but just to strategic approach from the OEMs, which prevent us to play a more significant role. This is one challenge, and then definitely the other challenge, technical challenge, is related to carbon fiber, the availability of the carbon fiber and the processing of the carbon fiber. And there I don't. Again, we're working hard to further improve the concepts of manufacturing, the designs. But the problem is the carbon fiber is not produced in Europe. So there we entirely depend on productions in Korea, Japan, North America. And also, yeah, the availability of the it is not sure at what price the carbon fiber can be delivered in five years from today, and what production capacity will be available by then.
Okay, perfect. Thank you very much, Axel. Understood. And thank you again for this presentation, and congratulations for the good work.
Thank you.
We are going to move on now to manufacturing, two manufacturing projects. We heard earlier that even simple components that are needed for fuel cell systems can be problematic to be found in Europe. And there is being a number of projects supported by the Fuel Cells and Hydrogen Joint Undertaking that helped us to improve also the European supply chain, its competitiveness and offer in the market. So we will start with the Imbalance project, and I'm glad to have here with us today Jose Garcia Campos, who is the coordinator of the project Imbalance, and will tell us a little bit more of what you have been doing here in this project, which is dedicated to innovative cost improvements for balance of plant components of automotive PM fuel cell systems. A complicated title. Let's see if you can explain us a little bit better what this is all about. Thank you.
Thank you. I cannot see the presentation yet. Yeah. Okay. So good afternoon, ladies and gentlemen. My name is Jose. I am a researcher at IESA Foundation. IESA Foundation is the entity in charge of the coordination of Imbalance project. Today, my colleague Consuelo Mora, who is the project coordinator, Imbalance project coordinator, cannot participate in this session. So sorry for that. First of all, before beginning this presentation, I would like to thank to the FCH for giving us the opportunity to share with you the contribution, the achievements achieved during the execution of this project. So thank you very much, FCH, for give us the opportunity, and thank you, Pietro, for the opportunity of presenting these results. Well, let's start with the presentation. In this first slide is shown some details about Imbalance project in terms of the core topic in which the proposal was applied, some information about the dates, the percentage of implementation, and finally about the budget. Well, this proposal, imbalance proposal, was applied to development of industrialization-ready proton chain membrane fuel cell system and system components some years ago, especially in 2016. This project started at the beginning of 2017, and this one finished at the end of October 2021. So today, the level of implementation of this project is equal to 100%. So this project was finished. In terms of budget, the budget for this project was around 6 million euros. The contribution of the fuel cell hydrogen joint undertaking was around 5 million euros. Please, next slide. Okay, in terms of partners, the number of partners for this consortium was 9. The first one was CVT, China Eurobical Technology, which was in charge of the integration of the overall system in powertrain and testing this one into their facilities. CVT is from Sweden. STEM-based from Germany was in charge of the dissemination and exploitation of the results. Celeroton from Germany too was in charge of the design, building, and testing the turbo compressor. IESA Foundation from Spain was in charge of the coordination and also manufacturing-oriented design optimization. UPC from Spain too was in charge of the advanced control algorithms. ABL from Germany was in charge of the designing, building, and testing of the cathode module. DLR from Germany too was in charge of the building and testing of the thermal module. ROS from Germany too was in charge of the designing, building, and testing the cathode module. And finally, from Sweden, PowerCell was in charge of the optimized layout of the fuel cell system, and also was in charge of the testing of this system in their laboratories. Please, next slide. In this slide is shown the main objectives were covered through the execution of imbalance projects. The first one was the scale up and enhance an innovative fuel cell system layout. Then to develop a cost-effective and improved automotive control unit. The third one was the design and development of a new cathode module. The next one was the development of a highly efficient thermal module. Then another one was the integration, testing, and evaluation of the new BOP balance of plant components. The optimization of the design of the BOP component was also one of the objectives of imbalance project. And finally, the last objective was the development of a reliable technology plan and implementation of the corresponding exploitation strategies and activities. Please, next slide. Okay, in this slide is shown the overall architecture of imbalance project. Well, the cathode module is in charge of supplying the air to the fuel cell stack, while the anode module is in charge of providing the request amount of hydrogen to the fuel cell stack. As results is produced electricity, which is transferred to the powertrain, and also water is produced as a result. The control unit can be seen as the brain of the system, is in charge of maintaining the operation of the fuel cell system, and also in charge of detecting errors at an early stage. Regarding the thermal module, aims to keep the temperature of the fuel cell stack at an optimal temperature, and also to manage the temperature of the air supply and the hydrogen supply by the cathode and anode. Please move to the next slide. Okay, in this slide, I would like to provide you an overview and the contribution of imbalance project regarding the state of the art. In the left side of the slide and on the right side of the slide is list some potential application and market area of the obtaining resource during the execution of imbalance projects. For example, regarding to the anode module, the obtained results, the obtained anode module permit to reduce the number of components and using a model based on gas management. Regarding the contribution of the cathode module related to the state of the art, it was obtaining a high-speed turbo compressor, which is characterized by oil-free air supply. This one permits a long lifetime, low weight, among other features that you can, I am going to show you an overview then about the compressor, the compressor. Regarding the management system, it was obtaining an antifreeze module that prevents the ice formation during the cold storage and reduce the shutdown procedure time. Regarding the control unit or the control system related to the state of the art, this control system, as I said previously, ensure large lifetime for the fuel cell system and lower operating costs for the fuel cell system too. In terms of future or application or market area, anode, cathode, or thermal management module can be used in other type of transport application, such as truck, maritime, even flight. Please move to the next slide. Okay, in this slide and in the next one, I'm going to show you some innovation obtained during the execution of Imbalance project. There are more than 3 in this presentation. I only provide you 3 of them, but we consider that 3 innovation must be highlighted. For example, regarding to the anode module, it was obtained an optimized ejector for automotive fuel cell stack that leads to a better fuel supply and hydrogen recirculation, as well as reduce the parasitic losses, among other features. Regarding to the cathode module, the high-speed air compressor for automotive fuel cell system. This compressor is characterized, as I said previously, by oil-free air supply, long lifetime, low weight, and high operating efficiency. I mean, among other features. Please, can you move to the next slide? Another innovation obtained during the execution of Imbalance project was the antifreeze module for automotive fuel cell system. This innovation was developed by one of the partners, DLR. The ejector I didn't explain before was developed by ABL, and the compressor was developed by Celeroton. Sorry for the mistake. Regarding the antifreeze module for automotive fuel cell system, this one prevents the ice formation during the cold storage and reduce the shutdown procedure time. Also improve the lifetime of the fuel cell system and reduce the degradation of the fuel cell. Next slide, please. Well, this project was divided into 4 different phases or steps since the beginning of the project until the end of this one, which are represented here in this diagram with 4 different colors: orange, blue, green, and yellow. Regarding the first step or phase, in this first step, was defined the most important parameters and overall architecture of the system. In the second step or phase, was carried out the design of the anode, cathode, and thermal module beside the control module. It was built the first prototype, and this one was tested. In the last step, all the components were integrated into the fuel cell system, and also in a vehicle to the end, or to finalize this step. The system was tested under real automotive conditions. Okay, next slide, please. Next slide, please. Can you move to the next slide, please? Please, can you move to the next slide?
There is Jose, a technical issue. I've been informed. Maybe you can continue with the oral explanation while we are trying to reload the slides. Hopefully, you have rehearsed enough to remember what was next.
Okay, so but you are
Because there
hearing me,
is some lessons learned.
you are hearing me, yes, no?
Pardon?
You are hearing
Yes,
me.
there we go.
Okay, so I finalized to explain the project schedule, and now it's time to the risk and lesson learned. Well, now we can see the presentation. Okay, so regarding the risk, COVID-19 pandemic represent an enormous challenge for all of us, also for the consortium of imbalance, because of many of the offices and especially the laboratories of our partners were shut down for a long period of time. The production lines also were stopped. That represents an enormous problem for us. And this represents a delay in the execution of the project, and also the sending parts across the border was more difficult than usual, and was more consuming time than usual. I mean, this is one risk among many of them. Regarding some lessons learned, I could hear some of them, again, among many of them. For example, regarding to the cost optimization, this technique conduct to identify potential cost reduction in production, especially for the most expensive component of the system, the air turbo compressor. The testing permit us to identify potential for improvement to be taken into account in the future. Again, some lessons learned among many of them. As you can imagine, this project finished at the end of October, and the partners learned many things about it. Please, next slide. Okay. In terms of communication and dissemination activities, this project is too active in these terms. For example, many newsletters, press releases, flyers have been released during the execution of the project. We have our own YouTube channel. We have obviously our own web page on the internet. This is the email. If you want to find more detail about the project, you can consult it. Also, we have our own Twitter and LinkedIn account. And the member of the consortium also participates in many conferences, and also release some articles and in journal conference and international conference. A total of 11 articles have been released during the execution of the project. 2020 was the best year in terms of publication. Please, can you move to the next slide? Okay, another point that I would like to highlight is that the Imbalance project has its own guidebook. In this one is presented the main project activities and also the results obtained during the execution of the project. I invite you to look up this guidebook if you want. In this guidebook also contains an overview of the current market for hydrogen vehicle and the future challenge in this field. Can you move to the next slide, please? And to finish this presentation, I would like to show you this image that which was obtained from the testing phase, and we have a car that runs independent on hydrogen. Next slide, please. That's all from my side. thank you very much. Again, thank you very much for your attention and for inviting us to share with you this our knowledge.
Jose, thank you very much for this very interesting presentation. I am glad to see that there are so many innovations coming out from the e-balance project with so many potential applications. So it's not only light-duty vehicles, as you have highlighted, there are also potential application maritime or even stationary applications. There is one concept that is sometimes touched upon in these manufacturing projects, which is the design for manufacturability. And one of the people that is following online was asking, well, what do you mean exactly with the design for manufacturing? Can you give some example concretely on how that has an impact on how you develop then some subcomponents?
Yeah, here this is a good question, and thank you for the question. I am going to provide you my corresponding answer. As you will know, in this project is in charge of among other tasks, is in charge of manufacturing some components. One of them is the compressor. So the compressor is, at the beginning, was one of the most expensive components regarding to the BOP components. In this project, we developed a prototype which fits with the features demanded by the fuel cell stack. But in a second round, it was developed taking into account the obtained results. It was developed a new turbo compressor based on the experience on the testing, which is cheaper, maintaining the same feature than originally was designed. So this is my point.
Okay, perfect. Thank you very much, Jose. There are some other questions, but we will see if we have the time to tackle them at the end when everybody has done his presentation. We now move on with another manufacturing project, and I would like now to give the floor to Joël Pochet, who is the coordinator of the project DigiMan, who stands for Digital Material Characterization, Proof of Process, Auto Assembly. Again, we have a rather complex title, but I'm sure that Joël, you will be able to tell us more about the DigiMan projects and its results. Please go ahead.
Yeah, thank you very much, Pietro, for this introduction. Thank you also to FCGU for the invitation. So yes, I will explain to you briefly the context and the results of the DigiMan project. So this slides have been prepared with the support of Tony Wilson from Intelligent Energy, but we cannot attend today, so I'll put a time for that. So the project means digital manufacturing and proof of process for automatic fuel cell stacks. So yes, it's quite a complex project, product name, but the project deals with the topic one in the 2016 call, dealing with manufacturing technologies for PMIC stack components and stacks. So it started beginning in 2017 and ended in June 2020. So it is a fully completed project. The budget was around 3.5 million euros, fully funded by FCGU. And if you can move to the next slide, please. We can go through the different partners. So the partners are split in 4 countries, as you see, UK, Germany, France, and Belgium. So next slide, please. We have 3 industrial companies. So the first one is Intelligent Energy in UK, who is also technical leader, because in fact this project aims at improving manufacturing production line of one of the stack from Intelligent Energy, which is an air-cooled stack, which is called AC64. So Intelligent Energy acted as a technical leader and also supplied the project with different information dealing with the manufacturing lines, and also was involved in the proof of process of the assembly, automation of the cell assembly, and also performed different AC64 stack tests. The second industrial partner was in Germany, Freudenberg, which was also a major partner from the project because they were deeply involved in GDL manufacturing and suppliers with different GDL types of different manufacturing quality, and also they developed in frame of the project a very interesting visual inspection system, or in fact, something that would help analyzing and checking the different non-uniformities of GDL during their manufacturing. So I will give you some details on that. And the last industrial partner was Toyota Motor Europe in Brussels. They helped us with the stack specification for automotive applications, especially, and also they shared some information dealing with their knowledge on the stack manufacturing. Next slide, please. In addition to that, we also had two research and technological organizations, one in UK, Warwick University, who supplied the project with the proof of process for the cell assembly, the blueprint design of the full manufacturing line, and also made some other analysis of the influence of defects on expected events during the manufacturing line, during the manufacturing process, in a relationship with a digital twin of the manufacturing line. And at CA in France, we were coordinating the project, and we spent quite a lot of time on GDL characterization in order to see which kind of characterization could be relevant for online characterization. So you will see also some results on this. And also we were involved in single cell performance tests in order to check if we could make the difference between acceptable and not acceptable defects. And the last partner, next slide, please, was Pretexo in France also, who acted as an administrative support. So you can move to the next slide, which is a picture of the team involved in the project during one meeting. I think this one was at Freudenberg premises in Germany. So yes, next slide. So really the aim of the project is to develop a blueprint design of the fully automated manufacturing stack line and testing in order for suitable for AC64 intelligent energy stack. So the main outcome is to ensure that we could have an operational supply chain cost reduction with this kind of approach, consistent with Industry 4.0 protocols, by making a fully automated uplift to the existing manufacturing line at Intelligent Energies. So, for instance, the line at Intelligent Energy was fully automated, except, for instance, the cell assembly, and the aim of the focus of the project was to include a automated step of this cell assembly in order to have a fully automated manufacturing line. There are different progresses compared to the state of the art, the quality control of the GDL, and different digital engineering for the future assembly and process improvements also. You can move on, please. Next slide. So the blueprint design is developed in order to check if we are capable to produce up to 50,000 full set stacks per annum. So it is based on a digital twin, and to check also that all this will lead to a significant expenditure and operational costs during the manufacturing. The aim is to reach 1 TRL, which is to raise from MRL 4, to MRL 6, and especially, as mentioned this morning, to reduce drastically the cycle, the cell cycle time assembly from 22 down to 5 seconds, and using having a material utilization higher than 99%. Next slide, please. Now we have some slides showing some research highlights. This first slide shows what has been done in terms of GDL online characterization, so mainly at Freudenberg premises. So in the top middle image, you see an image of the online visual inspection that has been installed at Freudenberg premises. On the right part of it, you see 3 red spots showing the location where some non-uniformities have been identified during the manufacturing process. And on the left-hand part, you see different kind of non-uniformities that have been detected. So now we are capable to see on both surfaces of the GDL to see where we do have non-uniformities, and then to put them in a database in which we have already defined some classical non-uniformities, and then to supply the customer with this kind of information via a database related to the part of the role they are buying or to the full role. So location and type of defect. In the bottom part of it, you see one attempt of including also a way to see non-visible non-uniformities. So this is based on thermal radiography, and this is also based on some internal work we have done at CA. You will see that in the next slide, in order to combine different kinds of non-uniformities, either visible or non-visible ones. And on the right part of the slide, you see that we have also worked on kind of converting and sorting of these materials in order we have two options, either to give the information to the suppliers, to the customers, sorry, of which kind of defects are located and where they are located and which kind they do correspond to, but also to select the parts that do fulfill a kind of request of the supplier, of the customer, who could, for instance, have defined which kind of non-uniformity they do accept and which ones they do not accept. So next slide. At Warwick University, you see on the top right the proof of process of the cell assembly that has been fully designed and developed in relationship between Intelligent Energies and Warwick University. And this has been validated in the Warwick University's premises and then transferred to IEA's production line. So it is compatible to a fully production environment and allowing the raise from MRL4 to MRL6, so high production capacity. And also, you see on the bottom right, a figure of the digital twin and blueprint linked to the blueprint design of the manufacturing line, in which there have been different studies in order to see how we could manage some either defects from the raw materials used in stack assembly, or defects or during the manufacturing of some steps of the manufacturing, in order to still achieve the production capacity. So move to the next slide, please. So as I told you, we at CA performed some analysis on the digital material characterizations. So for that, our aim was really to see which kind of characterizations could be compatible with high production volume rate. So online characterization, because we have clearly seen that depending on the kind of non-uniformities that can be seen on real GDL, maybe they're going to have impact or not on performance, depending on the other materials, depending on the operating conditions or the flow feed design, etc., etc. So we need clearly to improve the material characterization, and we also need to improve our capacity to predict which ones would have an impact on performance or durability and which ones are acceptable. So we have seen that with in-lab measurements, we have seen that some X-ray 3D tomography can help seeing some different non-uniformities, but this is not compatible with high production rate. But thermal tomography could be, and this is what Freudenberg has started to use, because on the right-hand side, on the top part, you see a sample of GDL on which we do not see any visual defect. But on the bottom part, you see that with thermal tomography, we do see some non-uniformities which are not visible. So these two measurements could be helpful to define visual and non-visual defects. So you can move on, please. In order, all these could be linked with some physical models in order to relate the link between material characterization and assembly properties or defects, etc., with performance. So this is done, for instance, by combining online measurements, data mining, and from materials or also from assembly, based on neural networks compatible to Industry 4.0 protocols in order to have a kind of machine learning approach to help accepting or not during manufacturing kind of defects of different species. So this project was mainly focusing on GDL, but I think we could expect using the same kind of approach for other materials. So next slide. So as a summary, in the project, we have reached all the KPI that were defined. We have developed a blueprint design of the AC64 fully automated stack, compatible with 50,000 stack per annum, compatible to Emerald 6 stage, including digital cause and effects models to manage the fuel manufacturing or the function of the unexpected events that could happen during the manufacturing, reaching the KPI to have a cell assembly less than 5 seconds for each individual cell, and also validating at the end of this full process that all these modifications do not have any negative influence on the performance of the final stack. So I think there is one other slide. So thanks to this DigiMine project, Freudenberg and also Intelligent Energy have already started a lot of exploitation and dissemination impacts in terms of their business approach. So Intelligent Energy has already started before the project, but the project helped them to be a bigger partner to Suzuki for two-wheel scooters. Same for the two-wheel scooters also with their 4 kilowatts air-cooled stack is also tested now in UK. And based on these, they have developed or they are developing other stacks with a larger power, dealing with either heavy duty or light applications for flights, for instance, and also for stationary application. And clearly for Freudenberg, this project, DigiMine project, was a big support to improve the quality control of their product and supply the customers with much more information of the real properties, I would say, non-uniformities of their product to allow them to select and choose if they accept or not. I would say that now the next step would be for the different OEMs to define, but it's quite more complex, to define which non-uniformities dealing with the GDL material are acceptable or not acceptable. By acceptable, I mean, even if we do have some uniformities, this has no negative impact on performance. By not acceptable, is that these non-uniformities will lead to not accepted decrease of performance, for instance, and the same for the durability. But this is another topic, and this was not fully covered by the project that was not examined. So next slide, I think, would be the last one. So yes, thank you very much for your attention.
Thank you, Joel, for telling us more about DigiMine. Clearly a successful project with some quite impressive results. I was in particular picking up on the fact that the blueprint design for the fully automated cell assembly and testing of the fuel cell stack could lead to a decrease in the capex of 50%, and it's 66% more efficient in terms of operations. But so what's next now for this blueprint? Is this going to become like a real life line for the production of stacks within the Intelligent Energy assets with a capacity of 50,000 stacks per annum?
I don't think
the innovation is impressive. So
yeah. I don't think that is the current situation, but what I know is that I don't know if they've already started to do that or not, but clearly for them it is to reach this target, that is to say, to include these developments and improvements in their manufacturing lines in order to improve their manufacturing capacity. I don't know if they have already started to do that, because I think that all these would need some funding, and it will also depend on their market. But the market, especially for them, is rising up. So I don't know the next steps exactly. Sorry for that.
No, indeed. I guess that it's difficult to speak on behalf of somebody else, but I was curious because indeed we keep on hearing that there is a lot of demand coming up, and we have these very good results in terms of manufacturing. So of course, from our side, there is the willingness and the hope to see these to become like real concrete applications then, especially in terms of supplying the demand. There was another question from the audience that maybe you could help me to answer, Joel. So related to the manufacturing of the fuel cells, can the innovative manufacturing technique be applied for electrolyzers to reduce the manufacturing time and cost? So this is very specific what you have done here for the intelligent energy product, but is there something that maybe could be extrapolated and used for the manufacturing also of stationary applications?
I would expect this not to be related to the application, but more to the stack itself. Because what we did in the project, that we started from a semi-automated manufacturing line already existing at Intelligent Energy, for which we had numerous automated steps, but some other steps were not fully automated. For instance, the cell assembly was not. There was some human manipulation during this cell assembly. But before that and after that, including the tightening tests, etc., were already automated. So the project really focused on providing a proof of process of the cell assembly, potential automation, fully automated step of the cell assembly. And this was done by design and also by manufacturing a first draft, I would say, of the corresponding hardware. So I would expect that to be transferable to any other cell assembly, because for electrolyzers also we have the same kind of assembly. Materials are different, but I think it could be transferable. And also the other aspect for the blueprint design and the digital twin, I think that also could be used for other application or stack design. I don't really see how far would be the effort to do so, but I think that the approach could be realistic also for other stacks and applications.
Thank you very much, Joel. I'm afraid that we are running out of time. We have to bring to a conclusion also this session dedicated to the building blocks for the transport application. I hope that our audience found it interesting. We started with the journey, with this multimodal journey this morning to see all the different transport mode applications, so when we are demonstrating them on the roads, and we concluded to see how today David, Axel, Joel, and José are working now for the development of the components for the next generation. And I would like to wish all of you good luck and hopefully to see you soon in real life. So thanks everybody for staying with us, and goodbye.
Bye.
Good afternoon, ladies and gentlemen. I'm Pedro Guedes Campos from the Financial Engineering, from the Fuel Cells and Hydrogen Undertaking. Sorry, but the name is changing and we get confused. I'm the Financial Engineering Officer, and I'm really pleased to be here today to moderate a panel, which is very dear to the JET Undertaking and myself as well, Hydrogen Valleys. Actually, Hydrogen Valleys ensure and the delivery of the sector coupling, which is of utmost importance to allow local ecosystems to transition towards sustainability, energy sustainability. And with that in mind, once we have green hydrogen as a main energy carrier, it can be used for all sorts of end-use applications. So that's how great green hydrogen can be. In this session, we will go through the timeline of our 3 most emblematic hydrogen valleys. We will also profit from a presentation from a project selected under the Connecting Europe facility for transport, which, despite not being a hydrogen valley, at least not having the label, it is close to, and it will help for ecosystems to build up to the expectations of hydrogen valleys. So each of the 4 speakers today will have 20 minutes, which means that if they consume it, we will not have time to questions and answers. Hopefully, we will all be on time and we will have plenty of time to debate, because the interactive session makes it much more interesting. So, starting from the beginning, our 2015 call, let's hear from Jesus Simon and the project in the Orkney Islands in Scotland called Big Hit, building innovative green hydrogen systems in isolated territory, a pilot for Europe. Jesus, you're welcome to take the floor.
Yeah, thank you, Pedro. Okay, I'm not able to see my presentation. Okay, I think.
Can you see
it right now?
We see your presentation.
Okay, so thank you very much, Pedro, for the opportunity to present the Big Hit here. I'm Jesus Simon, project manager at the Aragon Hydrogen Foundation, and in the project coordination team of the Big Hit project, which main goal is to develop a green hydrogen ecosystem in the Orkney Islands in the north of Scotland. The Big Hit project started in May 2016. As you said, it was included in the call of 2015 of the FCAIU, called Hydrogen Territories. It is expected to be finished by April 2022, so in approximately 5 months. So we are in the last steps of the project. The total project budget was of approximately 30 million euros, with 5 million euros coming from the FCAIU and the other 8 million euros from other UK funds and directly from the partners. Next slide, please. Here you can see the consortium. There are local partners obviously involved in the project, the Orkney Island Council, the main public body in the Orkney Islands, pretty active in the project, the local community of Sapienside Development Trust, and 2 technical partners located in Orkney as well, Community Energy Scotland and EMEC, the European Marine Energy Centre. The Scottish Hydrogen and Fuel Cell Association is working in the project dissemination and replicability, and we have 4 manufacturers in the project. ITM with their hydrogen refueling station and PEM electrolysis technologies, Giacomini with their hydrogen catalytic boilers, Symbia Fuel Cell with their hydrogen range extender fuel cell vans, and Calvera, an Aragonese company that has developed trailers to transport high pressure gas in light duty trailers. A couple of research centers, the Technical University of Denmark, the DTU, and the Aragon Hydrogen Foundation, we are working on the project impacts, analyzing on project impacts, and there is a follower territory, Malta, that will be in the position to replicate the Big Hit concept in their territory in the future. Next slide, please. Here you can see the project summary. The Orkney Islands are an archipelago of 20 islands with approximately 21,000 inhabitants and with a huge resource of renewable sources, especially wind, wave, and tidal. In the recent years, before 2015, they realized about a problem or a necessity. They have an important annual curtailment from renewable sources, around 20–30%, with electricity grid overloaded and with a weak connection with the main island at the UK. So they started to think about a solution for Orni, and BitHeat is part of this solution. It's a transition to a local low carbon economy based on hydrogen as a local energy storage system, and using this hydrogen for electricity transport and heat demands. Next slide, please. Next slide, please. Yeah, thank you. Here you can see an schematic of the project. The hydrogen is produced in a couple of small islands in Edi and in Sapin Sea. It is green hydrogen coming from wind and tidal, and this hydrogen it is consumed. Part of this hydrogen it is consumed locally in a couple of buildings with hydrogen catalytic boilers, and the estates of hydrogen that it is not consumed in Edi and in Sapin Sea, it is transported to the Orni mainland, to Kirwal, using the trailers that I previously introduced to you and the ferries that are moving passengers and everything through the islands. In Kirwal, part of this hydrogen it is consumed in a 75 kilowatts fuel cell located at the harbor, providing heat and power to a building and also cool ironing for the ferries. And there is as well in Kirwal a hydrogen refueling station supplying fuel to the range extender hydrogen vans. Next slide, please. The project progress, as I told you, we are in the last months of the project. In the field of hydrogen production, the direct coupling of the wind turbine to the electrolyzer has been tested and technically works, but there is less curtailment than expected initially at the beginning of the project. So the amount of hydrogen it is not large enough as expected, and the consortium is looking for a different alternative to be able to produce more hydrogen with this facility. At the same time, in Edi, there is an upgrading of the electrolyzer of ITM that I will slightly talk about that before, directly aligned with the marinization of this kind of system to work in maritime environments. One of the main outcomes of the project it is the hydrogen logistics developed in the frame of the project. Hydrogen has been transported from Sapin Sea, the production site, to Kirwal, where it is located, the hydrogen refueling station and the fuel cell in the harbor, by ferry, passengers ferry. So this is a pioneer action at European level, and the consortium has reached all the certifications for maritime transport. Related to the other facilities, the range extender fuel cell vans has been tested. Hydrogen mobility has been tested at island level with local production, and more than 50,000 kilometers of running of these vans without major problems. At the same time, the hydrogen catalytic boilers has been commissioned at the local school and has been tested by the systems built by Giacomini, and the fuel cell to provide power at the local harbor has been integrated in the overall ecosystem. At the same time, providing cool ironing to the ferries and heat and power to a local building. Next slide, please. Here you can see some of the facilities. On the left side, you can see the hydrogen production site, the transportation of this hydrogen, the distribution using the trailers and the ferries, and in the middle you can see the Kirwal harbor. in which it is located, the fuel cell to supply heat and power to a local building, to a building in the harbor, and the cool ironing. On the right side, at the top, you can see the hydrogen catalytic boiler system in the school, and on the right as well, the hydrogen refilling station and one of the vans. Next slide, please. Related to the risk, challenge, and lesson learned, frankly speaking, this project has been quite challenging. A lot of risk has appeared, and we have been dealing with them. So the lesson learned related to the deployment of hydrogen across the entire value chain, aspects related to the legal framework, the logistics of moving this hydrogen through the islands, how to establish the boundaries, the interfaces between the different projects in a location, have been shared using the Hydrogen Territories platform, which is a learning cooperative platform that we have established in BitHit, and I will be presenting it in the coming slides. But I would like to remark a couple of lessons learned more from the technical point of view. The first one is in working in islands with hydrogen, and the redesign for maritime environments, it is highly needed in certain hydrogen facilities equipment. This is something that we have learned through the project. In fact, ITM right now, it's in the process of upgrading the ED electrolyzer to be able to cope with these maritime environments, making certain modifications. And the logistical challenge of developing hydrogen ecosystems in islands or in remote territories, it is also a challenge. It is quite important. So it is important to take care in the planning and in the budget about aspects like the geography of islands for hydrogen distribution, aspects like remoteness, access to materials, even climate, weather conditions. Certain delays appear due to the winter weather that stop a little bit the deployment at certain points. So it is important to plan accordingly, thinking in these circumstances, and have some contingency, even higher than maybe in other kind of projects that do not have this kind of features. About the other points, the operational competence in this kind of projects, it is high importance. Working the local trainer in upskilling. And next point, it is mandatory, it is a must. This kind of projects cannot work without the involvement of the local community. In our case, the support or the actions of the Orkney Island Council has been always pretty aligned with the project offices, and they have supported strongly all project activities. Last but not least, our next challenge, it is related to the exploitation of these facilities as a commercial project. So we are in the last 5 months, and we are right now in the situation in which we need a transition from an innovative actions, from a project that it is in the frame of a funded action with the support of a funding body, to a commercial project. So we are in progress. This is in the situation in which we need to do additional actions to move this innovation action to a commercial project. Next slide, please. Related to the exploitation plan or the expected impact exploitation at general level, again, the point that I previously mentioned to you, the facilities should be integrated in the overall Orkney hydrogen strategy. So moving it from this innovation action project from a funded project to commercial. And from the manufacturer's point of view, the marinization, the decoupling of a wind turbine and the integration with tidal of a pen electrolyzer from ITM has been an outcome. From Calvera, testing and certifying for maritime transport their multi-element gas containers of hydrogen electrolyzers, it has been a goal for sure. And at the same time, the standard fuel cell vans of Simbi or the hydrogen catalytic boilers of Giacomini has been validated at real scale in a hydrogen island. Related to the impact, BitHit has been the first of a series of European Union Hydrogen Valley project. So the lesson learned have paved the way or have support a little bit other initiatives like Heaven or Green Island that are going to be presented as follow by Maria, Patrick, Janke, and we are in close cooperation in these projects. And impacts as well, reduction of CO2 emissions in the islands, hydrogen economy that they had support building a hydrogen economy in Ernie, or their social benefits like high qualified employment, training, reduction of renewable energy sources, curtailment, etc. Next slide, please. So I would like to introduce to you what the Hydrogen Territories platform is, which, as I previously introduced to you, is a learning cooperative tool that will help members to understand how regions can successfully replicate the big hit concept, the hydrogen valleys concept in their territories. So we have a website, you have there the link. We have developed a replicability tool, which is a kind of pre-feasibility tool to analyze a potential business model in the different territories interested in be a hydrogen valley. And we are launching certain webinars to talk about the lesson learned of the Big Hit project till now in them. The platform is currently chaired by the Aragon Hydrogen Foundation and by the Scottish Hydrogen and Fuel Cell Association, but it is important to mention that the activities of the Hydrogen Territories platform are not going to finish with the Big Hit project. They will be a continuation of their activities in the other FCAU projects in Heaven and in Green Islands with the support of Enagas, of New Energy Coalition, with all of us being the board of this Hydrogen Territories platform. Next slide, please. And here you can see the topics of some of these webinars that we have already developed. Probably this presentation is going to be shared. You have there the links to the previous ones. The first one about the experiences of Big Hit Heaven or Green Island. The second one related to how to build your hydrogen valley or island project. Third one about safety and technical design of these hydrogen valley projects. There will be another one in January next year related to commissioning and operational experience. So that's all from my side, and thanks.
Thank you very much, Jesus. Very, very interesting. Indeed, the Big Hit is de facto the first hydrogen valley that the JU has supported, effectively addressing this the renewable curtailment on the island, while transforming these green electrons into a green molecule to feed zero emission applications for road, maritime, stationary applications, as you mentioned. So really great to see this rolling. This is indeed a great open air showroom. I would call it a flagship as well. And congratulations for all the awareness raising that you are making and also going and moving on into creating this Hydrogen Territories platform. Yet, if I can ask a question, given that it's an island and there are a lot of challenges for smaller ecosystems where you don't actually target fleets, for example, for mobility, you target one single vehicle and so on, the scale is not there. And therefore, it's very difficult to have a business case. So my question would be, now that you have gone through this, actually two questions. Now that you have gone through this, first of all, are you going to scale up the fleets of, let's say, ferries, vehicles for the municipalities, the stationary application for municipality buildings, and so on and so forth? Or, and that's the first question. And the second question would be, do you see the Orkney Islands and the Big Hit project as having already taken care of all the challenges that you faced, because you faced and you mentioned them, and now that the technology is more closer to the market readiness, not exactly off the shelf but close to, do you feel that others can follow your footsteps with less of and without falling into the same pitfalls that you felt?
Yeah, I think so. Related to the first question, I think, as you said, if you are thinking in small scale facilities or even equipment, it is always more challenging to find a business model. So the people in Norni is doing, the entities there, it is trying to have an overall ecosystem. So it is not just a fleet of vehicles. They are right now thinking in projects at the airport related to maritime transport. So if you cannot scale up, I have thinking maybe in just road transport, thinking scaling up to have an overall ecosystem. So I think is what it is in the process of being done in Orni, and I think it is quite important. And related to the other point, market readiness, yeah, I think when we started this project in 2015, the overall context with hydrogen technologies was far away from the point that we are right now. So probably we have, if we're thinking what we did at this moment, probably we have done things pretty different, but we have learned a lot, and we are in the process of sharing this knowledge with the community using the Hydrogen Territories platform. There are certain points in which probably we will have done things a little bit or slightly different, like maybe how to produce this hydrogen on the islands, maybe not directly coupling these electrolyzers to just a turbine. Maybe you can think more in connecting them to the overall grid, so you are helping to support all the energy system. And probably this is something that projects like BitHeat or experience in projects like Heaven or Green Island are going to put on the table, and the next Hydrogen Valley project probably are going to start from a better point than ourselves, with a lot of lessons learned and with a more clear vision about how to find these business models now that all the equipment is closer to the market.
Okay, just a very straight question. In terms of, from the audience, in terms of cost of hydrogen, euros per kilogram, can you hint some figure from what you're getting in under this project?
Yeah, the expectation is to sell the hydrogen between 10 and 12 euros per kilo. It is selling price, not hydrogen production price.
Okay, thank you very much. All clear. Thank you very much, Jesus, for this very nice presentation. Let's move forward to the next speaker. We will now proceed to the biggest demo project that we have launched until now, the joint undertaking. It's called Heaven, Hydrogen Energy Applications in Valley Environments for Northern Netherlands. And it's a project from our call of 2019. I invite, this presentation will be made by two speakers, Patrick Nuben and Jank Kappenberg. Patrick and Jank, the floor is yours.
Yes. Thank you very much. It should go to Janke first. I'll just wait a moment. I'll just start. Well, my name is Janke Kappenberg, and together with my colleague Patrick Knubben, we will be presenting the Heaven project today. Heaven is all about kickstarting an integrated hydrogen economy in the Northern Netherlands. And well, let's just start with a quick project overview, as you see on this slide. I think the main figures here to address is that we started in 2020, so we're about 2 years going now. The total project budget is about 83 million euros, with a contribution from the fuel cell hydrogen joint undertaking of 20 million euros, and public co-funding, which is under preparation, in progress, of about another 20 million euros. Next slide, please. Yeah, we have a large number of partners, as you can see here. We have that ranges from knowledge institutions to small businesses, large businesses. We have the university is involved. Most of the parties are from the Northern Netherlands, because we are really trying to implement a hydrogen valley. So with a lot of regional parties, local parties, but we also try to engage some international parties. So we also have parties from 6 other countries within Europe, also trying to establish replication. So involving other regions so we can replicate our hydrogen valley model towards other regions within Europe, with of course the and ambition to have Europe being one great hydrogen valley. Next slide, please. Yes, well, in the Netherlands, we have great support for green hydrogen, and this is illustrated by this picture here, a nice picture, which was taken at our Wind Meets Gas conference we held this year. New Energy Coalition held this conference, and we had our king, His Majesty Willem-Alexander, who you can see here interacting with our colleagues from FCHJU and discussing the hydrogen developments there. Next slide, please. So going into the project a bit more, the main objectives are establishing a hydrogen ecosystem in the Northern Netherlands region, where we are integrating hydrogen initiatives in a systemic approach to demonstrate sector coupling and so fuel cell hydrogen use cases at a regional level. All the hydrogen we are using in this project, so in all of the applications and all the production, is 100% green. So from renewable energy, electricity production by either wind turbines or solar panels. And then in the applications, we have all the relevant sectors. We have industry, we have heat and power demand, so heating in the built environment, and also mobility. Next slide, please. To just tap on the global positioning versus the international state of the art, the Heaven project offers a robust approach to construct a regional hydrogen valley model, enabling to become an integrated hydrogen economy. And we're in the top 5 tier of hydrogen valleys globally. We are collaborating with other European Hydrogen Valley projects like Big Hit, as we just had our colleague Jesus explain about in the previous presentation, and also Green Highlands, which will be the next presentation very conveniently. So we're trying to set it up as a collaborative process. Next slide, please. Well, the application and market area, let's go to the next slide, then I can better explain this. This is a schematic of the entire Heaven project, which I will take some time to explain. The Heaven project is set up in 4 clusters, which you can see on this slide. In the left, the upper left part is cluster 1, which is a geographically defined cluster. This all takes place in Eemshaven Delfzijl region, which is an industry region and a harbor. And there, in another project, an electrolyzer will be built. And in Heaven, we are facilitating this electrolyzer by implementing the electrical infrastructure for the for this electrolyzer. So the sockets of this electrolyzer, so to say, and also we will be building a pipeline here to transport the hydrogen across the industry area and the Delfzijl Chemical Park. Also, we are implementing a boat, a salt barge, which will be hydrogen fueled and will be transporting salt from the Delfzijl harbor to the Rotterdam. And then we have cluster 2. Cluster 2 is all about built environment. There we have a number of applications. So it's built environment and also storage. So let's start with storage. We have Gasunie at the Heistock location in Zuidwending. And they are piloting a salt cavern, the use of a salt cavern to store hydrogen. And they are running all sorts of tests, seeing in what way we can, such a salt cavern can be used for hydrogen storage, which is of course very relevant. Then we have built environments. We have a data center, which wants to be more sustainable, and instead of using a diesel-powered backup generator, they want to use a fuel cell hydrogen backup power. So that is implemented at the data center. Then we also have a whole district in Hogeveen. We have 100 newly built houses and 250 existing houses, which will be using hydrogen for heating, so with hydrogen boilers. And also a municipal building, which also be using hydrogen for heating, mixing hydrogen to their natural gas boilers. Then moving on to the third cluster, which you see at the bottom right. That is the Emmen cluster, which is once again more geographically defined. In Emmen, there are a number of developments. We have the GATEC Industry Park, which is also looking to be more sustainable and using hydrogen for steam generation. And we have an electrolyzer being built there. Shell is building that electrolyzer, and also a hydrogen refueling station. And the hydrogen from the electrolyzer will be transported to the GATEC Industry Park, and that pipeline is being built by Gasunie. Then, sorry, I'm just going to go to the fourth cluster before we go to the next slide. So the fourth cluster is the mobility cluster. In that cluster, we have a number of hydrogen refueling stations being implemented, and also a great number of vehicles. So we have over 100 passenger vehicles. We have heavy duty trucks, we have garbage trucks, taxis, so all sorts of vehicles. And of course, key here is to align the hydrogen refueling stations with all these vehicles, so they they come online at the same time. So because without vehicles, you don't have your business case for the refueling stations, and vehicles will not be able to be sold if there isn't enough infrastructure, if there aren't any hydrogen refueling stations. So in this integrated approach, in this project, we try to bring it all together so it can happen. And then surrounding all these very practical activities, we have a number of supporting activities. We have basically for each of these applications, we have supporting studies, which is being done in a work package led by the University of Groningen. And all these studies will come together in a roadmap towards 2050. And next to that, we also have some replication activities, as I mentioned before. So there, the parties from outside of the Netherlands are mostly involved, seeing if we can develop the replication model and trying to gather best practices and lessons learned from Heaven to be able to implement this Hydrogen Valley model in other European regions. Next slide, please. Yeah. So here you see that in the map of Europe. So left on the left-hand side, you see all the parties that are from the Netherlands, and then spread out, we have a number of parties from other parts of Europe, which are mostly involved in the replication studies. Next slide, please. So the progress, as I said, we started in January 2020, and we are about 25% on our way. We have had some delays because of COVID. Social distancing has been somewhat of a problem for some of the activities. As you can imagine, it's in such a collaborative project, it's hard to not be able to just meet, and also the travel restrictions are rather difficult. But given that, I think the 25% progress is we're well on our way and getting things started. Next slide, please. Yeah, then the risks, challenges, and lessons learned. Well, as I said before, main risks: delay of critical installation components due to COVID delays. There's some business case finalization problem for the electrolyzers, more time consuming. The construction activities have been somewhat delayed due to social distancing at work sites. And then some of the challenges: availability of vehicles, production capacities, implementation practice on local and regional level. That is something that we are we have some issues with policies not being in place yet, because we are really pioneering. So a hydrogen refueling station is not common practice, unfortunately, yet. So for some of the municipalities, it is quite challenging to get their policies in place and to know what to do. So this takes a lot of time, and also with the salt barge, there also the experience and the lessons learned are this. It takes a lot of time to get all the permits in place. So these are really challenges for us. In addition to getting all the co-funding, the public co-funding in place, getting everything sorted out with all the provinces, and getting it to work well. We see that there is a lot of willingness all around us, as I mentioned at the start, up to the level of our King, His Majesty. But still, if you get to the implementation, we see that it's hard to get all the policies and all the regulations in place. Next slide, please. So this is a nice picture just to give an illustration of the work that's being done. This is at the storage facility in Zuidwending, as I mentioned before, with the test pilot of storing the hydrogen in the salt cavern there. Next slide, please. So here I will give the floor to my colleague, Patrick, to tell you some more about the exploitation and impact and communication activities we have been doing.
Yes, thank you, Janke, and thank you for the excellent explanation. My name is Patrick Knubben. Let me give you some insights in the exploitation plan, etc. As you saw, we try to make some active pictures of the activities, which is actually quite hard in times that restrictive measures are sometimes dominating. But never mind that. We are getting ahead, and looking at the exploitation plan, we've given a lot of presentations on the results, especially the viability of certain results to internal stakeholders, and discussing with them also about what the next steps would be, and actually also triggering networking activities, because in general, we see that Hydrogen Valley works as a magnet. There are many parties who are interested in getting aligned, getting connected, and getting involved. And obviously that's a good thing, because it gives a lot of attention, and I think it really supports and underlines the fantastic proposition Hydrogen Valley is. I think we can see that in Big Hit. We will see that afterwards with Green Highlands and many others as well. So that's a good thing. We are working doing a lot of presentations on the results, on the technical operation, the clusters activities, on the rollout, of course, group discussions, all the necessary things. But we also try to get really clear on how to accelerate, be prepared for other things, and especially interesting is the participation of the public, because we are technocrats, at least I am, so I'm used to discuss things with technical people, but we have to involve the citizens more, and that's why also the activities, as Jesus mentioned, on the Hydrogen Valley platforms is so important, to get connected to the people who are going to use the hydrogen in any way, shape, or form. Well, now let's see what's the impacts on the region. We see that our region has a smart specialization strategy, as many other regions do. This hits on that tremendously, and we do see that hydrogen is becoming ever more recognized as a future sustainable and clean energy factor to, let's say, help us tackle and combat the climate challenges we have. Sector coupling is, of course, very relevant. We are doing projects in industry, built environment, and mobility, and it's getting far more integrated every time. So we do see that this prospect of Hydrogen Valley and hydrogen activities inside the valleys trigger a lot of regional activity. So people get involved, as I said. The impact on, let's say, regulatory codes and standards is, of course, very important, because sometimes regulations, codes, and standards are fossil-based. We need to hydrogenify them, make them hydrogen ready. So that's a point which we need to look very seriously. Looking at the environmental and societal impacts, we do see that the public and the businesses do see the benefits. On the environmental side, of course, CO2 emission reduction, but also the other pollutants like NOx, etc., and fine particles. Societal in our region is very, very dominant, because the region we started is the aspect that we have a very big natural gas reservoir, which will be stopped at the end of 2023, which gives us a problem if we don't have a plan. And hydrogen is our new plan, at least one of the plans. Same goes for employability. If you can build things, you have to maintain them. So a lot of people can get employed in this new business. And that also goes for other regions in the EU and on the European level. May I have the next slide, please? Try to get something
Patrick,
more done.
in the interest of time, please speed up a little bit your slides so that we can get to questions as well.
Yes, I'm getting through it, Pedro. Communications activity, as you see, a lot of activities have been done. We have given you an excerpt. Many more are there. May I have the next slide? Just giving you an indication. Next slide as well. Next slide, please. And the next slide. This is an excerpt of, let's say, our Wind Meets Gas conference, which our King opened. May I have the next slide? It's very active, and there are many synergies with other projects. This is just an excerpt. There are many more, and are particularly proud that we are one of the 3 flagships sailing to a sustainable future. And I think, Pedro, we have several more slides, but they will be made available to the audience. I think it will give you a glimpse on what we have done and what we are doing. But in general, to close up, Hydrogen Valleys is a fantastic model. It acts as a magnet, and we are very willing to reach out to everybody who wants to get involved, and we'll find ways to get the involvement done. And the final thing, we cannot do this without the help of Europe, and especially the fuel cell and hydrogen joint undertaking. And of course, in the next year, the clean hydrogen joint undertaking. Thank you.
And we're happy that you are with us. So thank you very much as well. Just very quickly, because you mentioned it, it seems that you kind of triggered a snowball effect in the Netherlands, because at some point, perhaps because of your awareness raising and so on, all of a sudden, all the Netherlands is looking into a different energy mix, an energy mix that is looking into transition, having as a backbone hydrogen. So would you consider that you have opened the Pandora box and now everybody's jumping on the same topic with you? And if that's the case, do you see the chances for your business cases to get profitable, more profitable in the future because of that and because of increased appetite from hydrogen customers?
Shall I answer it briefly, Janke? The answer is yes, Pedro. It is Pandora's box. It gets a lot of attention, and that's okay, because 3 years ago, hydrogen wasn't in any policy document in the Netherlands. And since 3 years, it has exploded. It's in every policy document, and I think it's rightly so, because it justifies and it clarifies the enormous effect green hydrogen can have on the transition. We need to step out of certain non-sustainable energy carriers. So this is good, and other regions have identified that, and I think it's a good thing. We are reaching out to them. We are open to collaborate with everybody within the capacity we have, of course. And in general, you see that the appetite, the logical and rational appetite for green hydrogen is increasing tremendously. And I think it's a good thing, because it's also a recognition of the European policies, who have been there for a longer time. And I think this appetite is fantastic. And now we need to increase the number of plates on our dinner. We need to have more vehicles. We have to have more fueling stations. In order to do so, we need to have more renewable production, solar and wind, and bring that to the industry, to the mobility, and to the built environment. And I think, it is so logical and so rational to take this step, as also the president at the opening speech of the Hydrogen Week explained. This is the logical thing to do. So we never mind the Pandora's box. Let's open it and get it out of the box, and get everybody on it.
Thank you very much, Janke and Patrick, for your presentation. Very inspiring. The next presenter is Maria Hen. She will be presenting another Hydrogen Valley, this time on an island, and following the topic that we launched back in 2020. This project is in Mallorca, in Spain, and it's called Green Island, development of a hydrogen ecosystem on the island of Mallorca. Maria, glad to have you today, and the floor is yours.
Thank you so much, Pedro. I would like to thank you, the FCHU, for supporting us in this project, for inviting me to present the Green Highland projects. So my name is Maria Jaén. I am the General Coordinator of the project Green Highland. I am working at the Renewable Gases Department at Enagás, and we are proud of coordinating this project. So this project, which is the Green Highland, it's regarding the core topic of the decarbonizing island using renewable energies and hydrogen, and its hydrogen island. The project started in January 2021 and is expected to finish in December 2025. The total budget of the project, the eligible cost, is about 20 million euros, although the total investment is about 50 million euros. So as I mentioned, we started this year. So we, is more or less, we have implemented about 15% of the projects. And we have a maximum contribution from the European Commission through the FCHU of 10 million euros. And we have other financial contributions for the IDAE, which is the Spanish Institute for Saving Energy, about 2.5 million euros for the development of the PV plants associated to the projects, and the rest of the contribution of the budget is covered by the consortium, the rest of the partners. So next slide, please. We are a large consortium. We are 30 partners from 11 countries, 9 from the European Commission, plus Morocco, plus Chile. So really all the hydrogen value chain is covered by this consortium. I am talking not only about the hydrogen production, hydrogen distribution, hydrogen end usage, but also about the regulation, about the training, and about the life cycle analysis, about the business models, about all the topics regarding the development of the hydrogen ecosystem, or the green hydrogen ecosystem. So next slide, please. This is a concept of our project. We have 2 PV plants. One is located in Lloseta, in Mallorca, which is located in Spain, and next to the hydrogen plant that will be built also in the CEMEX land. And we have another PV plant which is located a few kilometers for the hydrogen plant, which is located in Petra. So both PV plants will provide green electricity to the hydrogen plant, and this green hydrogen will be transported by 2 trailers to 6 end applications. We are talking about mobility applications. The public transport company in Mallorca, which is called MT Mallorca, it's going to develop or to purchase 5 fuel cell buses in order to include it to its fleet. And to operate it during the project, and after the project, they will continue with this activity. And if they have positive results, they are going to increase this number of hydrogen buses. We also have a hydrogen fleet of cars, of vans, that they're going to be developed within the project. So we are going to create and to build a hydrogen fuel station to provide this green hydrogen for the mobility applications. Then we have a hotel. We have Iberostar, which is one of the main Spanish hotel chains in the world, and they are going to include a 50 kilowatts fuel cell in one of its hotels in Palma de Mallorca in order to cover part of the energy consumption, electricity and heat that they have in the hotel. Then at the bottom of the slide, you can see the Puerto Balear, which is, they're going to include 100 kilowatt fuel cell in 1 or 2 maritime stations in order to provide green energy to this maritime station. On the left at the bottom, you see Lloseta Council, that they are going to include a 25 kilowatt fuel cell in one of the public buildings. And in the middle, you can see here the hydrogen pipeline and the injection of part of this hydrogen plant, green hydrogen into the natural gas grid. So regarding this part of the hydrogen injection into the natural gas grid, we are going to do it through a guarantee of system of this green hydrogen. We are going to guarantee the origin of this green hydrogen. So after completing the public information phase of the regulatory project for the partial transposition of the European directive that includes the regulation of the guarantee of origin system for renewable gas in October 2021, in Spain, the Spanish Ministry of Ecological Transition and Demographic Challenge expects the government to approve the guarantee system for the renewable gases in the first quarter of 2022. So I think that this will have a very positive impact on the development of green hydrogen ecosystem in Spain. So this is what is the concept of the Green Highland project. So I think that we can move to the next slide, please. Perfect. As you see here, this is the sites locations. We have 7 sites. The first one is the green hydrogen production plant at Lloseta. One thing I would like to highlight here is that this project have specific circumstances, because at December of 2018, Cemex, which is a cement plant, announced that they will close the cement plant in Lloseta. So this initiative is part of an agreement signed between the Ministry of Industry, Trade and Tourism in Spain, the Ministry of Transition in Spain, and the Balearic government, with some companies, which at the beginning was Enagas, Acciona, and Cemex, and Redexis, and then a lot of partners join us, and now we are 30 partners, as I mentioned before. So this is a reindustrialization project. So I think that is something that we would like to highlight, that this is one of the power that green hydrogen has. So it's something important to highlight. In the site 1, as I mentioned, is the green hydrogen production plant. In the number 2, you have the fuel cell in a public building in Lloseta. Then you have a hydrogen and natural gas blending station and the injection point to the natural gas grid. In number 4, you have the hotel in Palma. Then you have in number 5, the hydrogen refuel station in the public municipality company in Mallorca. And in number 6, you have the fuel cell at the maritime station in Palma, in Puerto Balear, which is in the Palma port. And then you have the hydrogen pipeline that we are going to develop within the project. So one thing that I would like to highlight here is that we are going to start this ecosystem. And the idea is to increase the ecosystem according to the hydrogen demand on the island. So these figures show you that we are starting covering some points in the island. The idea is trying to cover all the complete island, and of course the rest of the Balearic Island. And then one thing that we will discuss later on is about the replicability of this kind of projects. As I mentioned, we have 30 partners, and 7 from these 30 partners are different islands, from Portugal, from Chiloé, from Morocco, from Iran, from Greek, that they're going to replicate this green highland in their own territories. So this is an enormous powerful of the project that we are very proud of it. So next slide, please. To show you, although we have started this year, we are at the beginning of the project, we have made some progress that we would like to share with all of you. The first one is that, as I mentioned before, we are building 2 photovoltaic plants. One is located in Lloseta, next to the hydrogen plant, and it's about 8.56 megawatt peak. And the idea is that they're going to enter into operation by the end of this year. The other one, which is located in Petra, is almost 6 megawatt peak, and the idea is that it is going to start in operation by February of 2022. So next slide, please. And another important milestone for us is that electrolyzer will arrive by mid-December this year. I think that by 15th of December, the electrolyzer will be delivered in Lloseta. So we are waiting for that. And in the meanwhile, we of course are completing the engineering of the hydrogen plant. So here is a picture about how the hydrogen plant looks like. And the idea is to finish the shot test during this year. And we expect that the plant will be producing green hydrogen in the first quarter of 2022. So next slide, please. This is some key figures that I would like to share with you. The first one is that we are going to start producing 300 tons of hydrogen that is going to be produced and consumed in the island of Mallorca. And the idea is to increase this ecosystem according to the hydrogen demand up to 1,000 tons. So the idea is when the ecosystem will be completely implemented, we will be able to avoid a carbon footprint of more than 21,000 of tons per year. We are with this, not only with this project, but also as, for example, BitHit, Jesus with BitHit mentioned before, and Patrick and Janke with Heaven. When we are developing this kind of hydrogen hubs or hydrogen ecosystem, we are really developing a new direct and indirect employment ecosystem associated to green hydrogen, which is something that we are very proud of it. We are looking to develop sustainable, large-scale, island-based hydrogen hubs. So the idea is that once the project, or after this 5 first years of the project, that we are with the supporting of the FCHGU, the idea is to, of course, continue the project, increasing and improving the ecosystem and increasing this ecosystem according to the hydrogen demand on the island. Another key point that I would like to highlight is that we are going to develop a long-term roadmap where hydrogen will play a key role. We are working with the Balearic government in order to include the green hydrogen in their roadmaps about decarbonization, about energy transition, because we think that hydrogen will play a key role on that point. Another key figure that I would like to share, and I mentioned before, it's the scalability and replicability. These kind of projects are a very good example of how hydrogen ecosystem could be replicated in other territories. So 7 partners, as I mentioned, is going to study how they are going to replicate this in their own territories. I am talking about the European Union, of course, but beyond. I mean, I'm going to talk about Chiloé, I'm talking about Marruecos, I'm on Morocco. So it's something that we think it's very useful. And for example, we are working with Jesus regarding the hydrogen territory platform tool. This is something that he mentioned before. It's something that they started in the BitHit project, and that we are going to continue, and we are going to improve this tool within Green Highland, because we really think that it's a very useful tool for the territories to really try to evaluate how they could develop this kind of hydrogen ecosystem in the territories. And as I mentioned before, the last point that I would like to highlight is that this kind of projects really have a very large investment associated. So in this case, we are talking about 50 million euros. So there are large projects with the idea to start large ecosystem and to start new actions and to try to push to other hydrogen ecosystems to be developed. Next slide, please. Just to highlight that in this project, we are considering 3 pillars. The first one is the development of hydrogen infrastructure, not only for the production, but only for the transport, distribution, and end users. So we are covering all the hydrogen value chain. Another key point is that we are going to develop this hydrogen roadmap in the Balearic government. And the third pillar for us is these replications. So we have structured the projects according to these 3 pillars. We are going in work packets 2, 3, and 4. We are talking about the hydrogen infrastructures. In work packets 5, we are talking about the model impact, about the life cycle analysis, and so on. And in work packet 6, we are talking about the replication, the scale up and the replication of this hydrogen ecosystem throughout Europe and throughout the world. And of course, there is always a very important topic on this kind of project, which is the communication, dissemination, and exploitation. So in the next slide, please, I will explain a little bit more these communication and dissemination activities. We would like to thank the President of the European Commission, Ursula von der Leyen, for highlighting the Green Highland project as an example to clean industry and reach carbon neutrality during the official launch of the European Sustainable Energy Week on 25th of October. And again, she mentioned the project of Mallorca during the official launch of the European Hydrogen Week last Monday. So I think that the hydrogen valleys and a specific green highland, in our case, we are trending topic. So this is a very important role from the point of view that we have to we have a strong commitment with the expectations that we are sharing with the rest of the community. And although we are in the first year, we have very good results regarding this communication and dissemination activities, because I think that people is really interested in green hydrogen ecosystem and how they can replicate and how they can design and how they can include hydrogen in their decarbonization and energy transition. So this is a few figures that I'm not going to go deep on that. So I would like to thank all the audience and all the people that are really following us through the social media. We have a LinkedIn group, so all of you are invited to join us and to follow us, because really we are in the first year, but I mean that the main things and the positive things comes during the following years. And just to give you here our website and some figures that maybe would be useful for you. So next slide, please. That is the last one from my side. Is regarding the importance of the synergies with other projects and programs. I think that Jesus and Patrick and Janke mentioned before, we are really developing a Green Highland hub. We are in a very close collaboration with many initiatives regarding green hydrogen projects and initiatives. For example, Heaven, for example, Big Heat, and another one, because we think that really combining efforts, we will multiply the results and we will reach much more people, and we will be able to help to develop this hydrogen ecosystem and to accelerate the implementation of hydrogen. So that's all from my side. So thank you so much for the opportunity.
Thank you, Maria, for this very nice presentation of what you're doing, and congratulations for the already being ready with the photovoltaic farms and the electrolyzer coming in as a Christmas gift. So congratulations for that.
Thank you.
We don't have time for questions, but let me jump to the last but not least panelist. As already mentioned, you will have a presentation on a project supported by the Connecting Europe facility under the call 2019. It's called Multi-City High. Mr. Louis Denous, thank you very much for being with us today and stepping in for your colleague, because I know that you had to jump in. Louis, please take the floor.
Thank you very much. Yes, I'd like to present you the Multi-City project, which has been launched by Hynamix. Hynamix is a subsidiary of the EDF group. So just let me check.
We're seeing the presentation, but you're muted now. You're muted. Louis, you're muted.
Okay. I am demuted. Thank you. So I was saying that the Multi-City project has been first submitted in August 2020 at the CEF, Connecting Europe Facility Call of Proposal, and thankfully it has been awarded by the SENIA agency, which is organizing this tender at the end of that year. All right. So just before going a bit more in depth and in the details of the projects, just I would like to share with you some key figures. So this is mandatory because it's demanded by the CEF program. The project, or more likely the projects in the project, have to be deployed by the end of the year 2023. The total capex of the project is estimated about 44.5 million euros. Which we have to subtract about 8.9 million euros, which is the CEF contribution. And to date, the stage of implementation is about 20%. as most of the work will be done and achieved by Hynamics in 2022. So they are about the figures. So next slide. The Monty project is in line with two major agreements. The first is the Paris Agreement, which was signed in the end of the year 2015, which aims at being below 2 degrees of increase in temperature by the end of the century, and at a European level, the EU 2030 climate target plan, which is aiming at reaching carbon neutrality by the end of 2050. So these are the main figures. The multitude projects aims at decarbonizing transportation and heavy mobility, which is one of the major target sector in order to reach this carbon neutrality. Of course, if today hydrogen technologies are mature, there is still a lag in European infrastructure, which comprehends both production, compression, storage, and distribution. And by deploying hydrogen ecosystems, like we are trying to do with this multi-step project, we will tackle those issues and accelerate the development of the hydrogen sector in Europe. That's what we want to do. So next slide. To achieve such a project, it is very important to aggregate the hydrogen demand in specific areas, which we will detail a bit more later, and also to maximize the hydrogen consumption per site. This is very important to get a viable project, both for the investors in the infrastructure, and in the end for the end users, the off-takers, who absolutely want to have a competitive hydrogen price. And all of that is made in order to, of course, maximizing the hydrogen and to minimize the greenhouse gases emissions at the end of the project. So next slide. All right. So there is so here you can see all of the projects which are within the project Multicity. So there are four projects which we are developing with 4 different cities. The city of Belfort in the Burgundy region, the city of Nice in Provence-Alpes-Côte d'Azur, the city of Nantes in the west coast, and the city of Gardanne close to Marseille in the south also. So both of those, all of those projects are a bit different, but they are mainly based on fleets, captive fleets, which is obviously important to get the revenue of hydrogen. I mean, we can't for now have an open and fully open station. We have to build our projects first by building fleets. So if we are going a bit more into detail, so Belfort is a project which is mainly made with buses, the buses of the cities, and we are also tackling at feeding the industrials of the region. There are 8 or 9 of them with green hydrogen. So this is the project of Belfort. In Nice, this is a very terrestrial hub. So we have buses, we have refuse trucks, we have trucks, and we are located in a hub close to the north of the city. And it's a very important project, a 2 megawatt project. Next, we have the project of Nantes, H2 Loire Valley. This is both a terrestrial and a maritime project. We are tackling at addressing the buses of the city and also the ships, which are also located in this area. And at the end, we have the project of Gardanne, which is a bit special. It's mainly trucks today, so we're not going to be able to. I mean, it's going to be the project which is going to take a bit more time to be developed because those uses are not as developed, of course, as buses or refuse trucks. So we have to wait a little bit, maybe a bit after 2023 to commission the station in Gardanne. So this is for this slide. So next slide, please. In order to achieve such a project, there is 4 major steps. In order, we have to tackle the power supply. So of course, as Europe is pushing in, and France too, we have to produce green hydrogen. Of course, we have to get green electricity because H2 is produced from electricity. So this is a very important part for us. There is many ways to get green electricity contracts, but it's very important for us because the subsidies come if you produce green hydrogen, and low carbon hydrogen is not enough in France to get subsidies and to launch a project. So this is the first step. Of course, the second and the first step are obvious, is to develop production units and also to launch some distribution units, which are obviously important to launch a project. And the fourth part, which is sometimes a bit disregarded, is the monitoring of the installation. So as you know, hydrogen is a special gas, as it has some risks. There is risk of explosion and inflammation. So you have to monitor quite well the station so that you minimize the risk for the people who are working in the station, for the clients, and for the people in general. And all of that maintenance has to be done on a 20-year period. So that has to be noted. Next slide, please. Yes. So the overall objectives of this project is to install overall an 8 megawatts of total electrolytic units. So it's quite yeah. So we don't okay. On 4 different sites with 4 different electrolyzers, 16 hydrogen supply points or hydrogen dispensers, and in total 4.8 tons of hydrogen stored on the station. And as I mentioned it at the beginning of the presentation, we have done only 20% of the overall job. Most of the job will be done by the coming year. Next slide. So here you can see, I mean, it's not very detailed as in the picture, but you can see how a nitrogen production, compression, and distribution station look like. This is the project of Belfort, which is located within the city center. So to refill the passes. So this is not very important, but just to see how the footprint looks like. We are about it's about a 3,000 square meter footprint. So it's not nothing. It's sort of an issue because in cities you have some lack of space, and you have to consider a certain amount of footprint to launch such a project in city centers and more generally in cities. Next slide. So what about the challenges? So we need, I mean, there is really 2 challenges for launching such a project. First, we need to have a massive hydrogen production to lower the cost of hydrogen and minimizing for us investors the risks, and of course for the clients to be able to refill the vehicles with hydrogen that is quite low in price and quite competitive compared to other green fuels, and of course compared to the actual diesel, which is of course very attractive economically. So this is the first challenge, and the second one is to implement a project which is close to transport access with strong industrial activities, where obviously the hydrogen demand is going to increase. And it's on those axes that we want to locate our project so that it has a bright future and it can expand in the future. And to conclude, some key figures on the next slide and the final slide. So as I mentioned it, we are producing about 8 megawatt equivalent of electrolyzers, which is very important. We are on 4 different sites. We are kind of mapping France as we have projects in in the northeast, northwest, and in the south. And overall, we are aiming at reducing the CO2 emissions by about 320,000 tons of hydrogen on the 20 years period on those 4 projects. So it's a very ambitious project. It's very difficult to be able to monitor those projects at the same time and to launch them at the same time. So the mandatory by CEF is to launch them by the end of the year 2023. We are still working on it, and most of the job is not done. We have to be conscious about this, and it will probably be done by 2022. And so this is how we want to bring our stone to the European ambition, and of course that's highly replicable as those cities and those specs are obviously available everywhere in Europe, and that's how we want to push this this filière. So,
Louis, I believe we lost you.
Thank you for.
Okay, you're breaking, Louis, but I guess you were close to finishing. Please stay there because I wanted to ask you something. But just to say that although focused on mobility applications, this project is rather large, and in fact it contributes. Okay, we're having you back. I was saying that this project is rather large, and it actually works on 4 different sites in France, which can become hydrogen hubs later on, and close to the concept that we have for hydrogen valleys. Once you start having the demand for hydrogen, or actually if you supply the hydrogen, then the demand for hydrogen will pick up, not only for mobility applications, but also for other areas. In that regard, the fact that it's sitting in 3 different corridors of the TEN-T, of the Trans-European Network corridors, it's also very welcoming, because in that sense it becomes the backbone. They will contribute, these refueling stations will contribute to be the backbone of more demand and circulation of vehicles around Europe. So congratulations for that. Actually, we don't have time for questions, but I would like to say that and final remarks to say that as exemplified today, the joint undertaking has long understood the potential of regional ecosystems like the ones that we saw today, and we kickstarted it with Big Hit and then the other projects that followed. It's really a pleasure to see these being picked up worldwide. We keep on using European money to ensure that it's green hydrogen that comes out of these hydrogen valleys. So we support green hydrogen valleys in that respect, and this is very good that we focus on this and Connecting Europe facility as well, because otherwise we will not achieve our targets. I would like to thank everybody in the panel, Jesus, Maria, Patrick, Young, and Louis. Very many thanks for being there today, and congratulations for all that you have been doing until now. From our side, the Clean Hydrogen Joint Undertaking, we will do our best to continue helping you and other projects on the replicability path that you are going forward with, and perhaps new calls, new flagship projects, but also project development assistance to ensure that regions that are not yet at the place where you were when you applied to us, they also get support to build up their business cases, and then hopefully be able to tap into EU funding sources later on. So thank you very much. And,
thank you so much.
This was the last session of today. The next session will be at 9:30 tomorrow. It will be the last day of the program review days, but also the last day of the European Hydrogen Week. So please be there, and it will be a pleasure to see you again. Bye.
Thank you all.
Thank you. Bye.
Thank you.